Before the first atom, before the first star, before space had room to expand or time had a second to tick, reality had no stage at all. Yet, something happened. The Big Bang didn't just ignite the universe, it drew the first line between nothing and everything. So what could possibly cause a beginning of space and time, and can physics even look behind that first flash? Every origin story we tell relies on a clock, a stage, and a chain of reasons. But at the universe's frontier, those familiar props begin to dissolve, leaving physics to speak in hints. We live inside an expanding archive, a cosmos that keeps its earliest chapters encoded in light, in elements, and in motion. When we measure distant galaxies, we're not just mapping space, we're reading time, line by spectral line, and when we tune in to the microwave afterglow that fills every direction, we're hearing a faint, persistent echo of a hotter state. Yet the closer we push toward the first instance, the more our best explanations start to behave like boundary markers, not destinations. This film follows that narrowing path with care, because the Big Bang is both one of science's strongest models and one of its sharpest limits. It is not a story of matter flying outward into pre-existing emptiness, but of space-time itself changing scale, carrying energy and information along with it. The evidence for a hot, dense beginning is astonishingly precise, and it arrives from separate directions that should never have agreed by accident. Still, the same equations that guide us backward also warn us where they stop being trustworthy, where gravity becomes too intense, temperatures too extreme, and the very concept of a smooth space-time may fail. So we will ask the question that refuses to stay simple. If the Big Bang describes the universe's early state, what can science honestly say about the conditions that made that state possible? The word cause is deceptively ordinary, and in cosmology it can mean many things: an earlier event, a deeper law, a constraint on what is allowed, or a boundary condition that does not unfold in time at all. To get there, we begin like detectives, not philosophers, tracking the redshift of galaxies, the ladder of distances, and the quiet geometry written into the sky. We examine the cosmic microwave background not as a pretty picture, but as a map of primordial sound waves frozen into radiation. We test the universe's first minutes by counting the light elements, and we take seriously the tensions where predictions and measurements do not perfectly align, because anomalies often point to new physics. Then the journey steepens. We descend into the first fractions of a second, where familiar particles dissolve into hotter symmetries, and where the universe becomes a laboratory no human machine can fully reproduce. We confront the Planck scale, where our two great frameworks, general relativity and quantum theory, must somehow share a single description, or surrender their authority, and we meet an idea that may have reshaped the entire cosmos in an instant: inflation, an episode that can explain remarkable features of the sky while raising a more unsettling question about what came before it. At that edge, even nothing stops meaning what it means in everyday speech. In modern physics, emptiness can carry structure, fluctuations, and energy. It can be calm in one description and restless in another. Some proposals treat the beginning as a quantum transition, others as a rebound from an earlier cosmic phase, and others as a boundary where time itself becomes an emergent concept. Each possibility brings a promise, and each demands a price: new fields, new principles, or new ways of deciding what counts as an explanation. We will not offer a single neat culprit because the universe does not owe us a simple narrative. Instead, we will build a map to the limits of inference, separating what is measured, what is extrapolated, and what is imagined with mathematical discipline. And as the boundary draws near, the central mystery changes shape, becoming less about finding one hidden event and more about understanding what before, after, and because can mean when the universe itself is the arena in which meaning occurs. This is a journey to the first page of reality, and to the margins where pages may not yet exist, where the laws we trust are tested, and where the question of origins becomes a question about time, about nothingness, and about whether causes can exist without a world to contain them. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will move from the hard evidence of a hot beginning into the first instance where physics blurs, and then into competing ideas that try to replace a singular start. Along the way, you'll see why the most honest answer may be a boundary of meaning, not a missing name. Before the first star, before the first atom, before any clock could tick, the story points toward a boundary. We call it the beginning, yet the word hides a trap, because a beginning usually means a moment inside time, happening somewhere in space. The Big Bang challenges both assumptions at once, and it does so with a kind of mathematical indifference. We open with the simplest, most unsettling motif: no space, no time, no familiar stage where events can unfold, no coordinates to hang a sentence on. If there is no time, the phrase "before the universe" may be meaningless, not just unknown. If there is no space, the phrase "where did it happen" may be misdirected, like asking where a melody is located. Yet our minds keep reaching for a cause, because causes feel like the grammar of reality. The central question is not just dramatic, it is technical, and the technicalities matter. If the Big Bang marks the beginning of our observable universe, what can science say about what caused it? And if science cannot answer, what exactly blocks the answer? Missing data, missing theory, or a category error in the question itself? The stakes are high because the question tests the limits of explanation, and it exposes what we mean by why. Popular imagery offers an easy picture that is mostly wrong. A bomb goes off at a point, debris flies outward into empty darkness, and the universe is the expanding cloud. That picture assumes pre-existing space, pre-existing time, and a privileged center, as if the cosmos had an address. Modern cosmology does not describe the Big Bang that way, and the difference is not a detail. In the standard model, the Big Bang is an early, hot, dense state of the universe. It is the expansion of space itself, not an explosion inside space, and the distinction is encoded in the geometry. Galaxies are not shrapnel racing through a void from a central blast. They are, on large scales, carried apart as the metric of space-time changes, like dots on a stretching fabric. A useful visual is not a fireball, but a grid. Imagine a coordinate grid drawn across the universe, then watch the grid lines drift apart everywhere at once. In that picture, no point is the center, because every point sees others receding as the scale changes. The expansion is not about matter rushing outward through emptiness. It is about the ruler you use to measure distance quietly lengthening with time. This is why the question, "what is the universe expanding into?" can mislead. Expansion is not necessarily motion through an external arena, the way smoke expands into air. It is the stretching of distances defined within the universe, so the geometry itself is doing the changing. The edge is not a wall you could reach, and the center is not a place you could point to. Even the word "nothing" needs careful handling here, because everyday language smuggles in hidden assumptions. In ordinary speech, nothing means empty space with no objects, a dark room with the lights off. In physics, empty space is still a thing, with fields, energy, and quantum fluctuations that can be measured. When cosmologists say no space and no time, they are not casually claiming a simple nothingness. They are marking a limit where our usual concepts stop working, and where the equations ask for a new vocabulary. So what does the Big Bang theory actually claim in its careful form? It claims that the universe has been expanding and cooling from a much hotter, denser past, and that this evolution is governed by well-tested laws. It claims that this history leaves measurable traces in the sky and in matter, traces we can still read today. It does not, by itself, claim to describe an absolute origin from literal nothing. It does not automatically answer why there is something rather than nothing, even if it explains how that something evolved. To understand what we can ask, we start with what we can observe. The first pillar is cosmic expansion, discovered through the redshifts of galaxies and sharpened into a quantitative relation. In the 1920s, observations by Edwin Hubble built on earlier insights by Georges Lemaitre, who connected redshift to an expanding universe in relativity. The Hubble-Lemaitre law links distance and recession speed in a simple pattern. Farther galaxies show larger redshifts, indicating that space between us and them has stretched. Redshift is not just a Doppler effect in the everyday sense, like a siren changing pitch. In an expanding universe, light can be stretched along with space, so its wavelength lengthens as it travels. Astronomers measure this stretching by comparing spectral lines, atomic fingerprints, against laboratory standards. This is not a single measurement, but a broad framework confirmed across many surveys, using galaxies, supernovae, and other distance indicators that cross-check one another. Expansion also implies a past that was smaller, denser, and hotter. because the same amount of energy was packed into less volume. Run the equations backward and the universe compresses toward an early state, with temperature rising as the scale factor shrinks. That backward extrapolation is not a movie of objects converging on a point in space. It is a statement about the scale factor of the universe shrinking towards zero in the simplest models, and about density increasing as geometry tightens. The second pillar is the cosmic microwave background. It is the afterglow of the early universe, now cooled to microwaves by expansion, and it arrives from all directions like a faint ancient fog. It fills the sky with extraordinary uniformity, with tiny anisotropies that encode early density variations. Those variations later grow into galaxies and clusters under gravity, turning microscopic differences into cosmic architecture. The CMB is not just a relic, it is a precision data set, and precision is what turns mystery into science. Its spectrum is close to a perfect blackbody, matching the prediction of a hot thermal origin, and that near perfection is itself a clue. A blackbody curve means matter and radiation were once in equilibrium, colliding so often that they forgot their initial conditions. When the universe cooled enough for electrons to bind to nuclei, forming neutral atoms, photons stopped scattering freely. Light decoupled from matter, and the universe became transparent, leaving a snapshot we still detect. Its angular power spectrum maps sound waves in the primordial plasma, frozen into patterns at recombination. These were pressure waves, driven by the tug-of-war between gravity pulling inward and radiation pressure pushing outward. The peaks and troughs in the spectrum are not artistic flourishes. They are a record of physical scales, densities, and compositions, written in temperature variations of only tens of microkelvin. The third pillar is primordial element abundances, a kind of chemical fossil from the first minutes. In the early universe, temperatures were high enough for nuclear reactions, but the window was brief as expansion cooled everything rapidly. Big Bang nucleosynthesis predicts specific ratios of hydrogen, helium, and traces of deuterium and lithium. Observations of ancient gas clouds and old stars broadly match these predictions, within known tensions that remain active research questions. This agreement anchors the model to chemistry written before stars existed, when the universe itself was the furnace. Together, these pillars do not prove every detail, but they establish a strong core. The universe expanded from a hot, dense state, and that claim is supported by independent lines of evidence. It cooled, formed atoms, released the CMB, and later formed stars and galaxies, which then forged heavier elements in their cores. The Big Bang theory is, at minimum, a successful account of this evolution, and its success is why the origin question becomes sharper rather than softer. But the word beginning still sits uneasily on top of the evidence, like a label placed too early. The pillars point back to early times, not necessarily to the first moment, and they do so with diminishing certainty. They tell us what the universe was like when it was seconds old, and even fractions of a second old under certain assumptions. They do not automatically reveal what happened at time zero, or whether time zero exists as a meaningful physical boundary. Here we meet the boundary of evidence and the boundary of theory. General relativity, when pushed backward, leads to a singularity in the simplest solutions, where curvature and density diverge. A singularity is not a place we can visit, it is a sign that the equations have been driven beyond their domain. It signals infinite density and curvature, which usually means the model is incomplete. Physics treats that as a warning label, not a final explanation, because infinities often mark missing ingredients. Quantum mechanics enters because the early universe was extremely small and energetic, where the smooth spacetime of relativity may become grainy or uncertain. At sufficiently high energies, quantum effects of gravity should matter, and the relevant scale is often described by the Planck length and Planck time. Yet we do not have a complete tested theory of quantum gravity. We have candidates, approximations, and partial frameworks, but no single confirmed description of spacetime at the Planck scale. That gap is where many cause of the Big Bang stories live, and where confident language can outrun the evidence. It is also where the meaning of cause becomes unstable, and that instability is not philosophical decoration. In ordinary experience, a cause comes earlier in time and produces an effect later, like a match producing a flame. If time itself is part of what begins, then earlier may not exist in the usual sense. Some proposals replace temporal causation with boundary conditions, or with deeper laws that do not require a prior moment. Others keep a form of causation but embed it in a larger space-time where our universe is one region, a local chapter in a bigger geometry. So we need a disciplined way to ask the question, because undisciplined questions generate undisciplined answers. We separate 3 layers that often get mixed together, especially in popular retellings. First is the evidence for a hot expanding early universe, which is strong and measurable. Second is the extrapolation toward earlier and earlier moments using known physics, which is powerful but conditional. Third is the speculative domain where new physics may replace the singularity and redefine what beginning means, which is exciting but not equally confirmed. We also need to name what the Big Bang is not, because misconceptions can harden into false dilemmas. It is not a claim that the universe popped into existence from philosophical nothingness, as if from an empty box. It is not a claim that science has already explained the ultimate origin, even if it explains much of the early evolution. It is not a claim that there must be a first cause in the familiar sense, because familiarity is not a law of nature. The Big Bang model is powerful, but it is not the final word on why there is a universe. Still, the model gives us a timeline with remarkable reach, and the timeline has texture when we slow down. We can describe the universe back to recombination, about 380,000 years after the hot beginning, when atoms formed and light decoupled. We can describe earlier plasma physics, when photons and matter were tightly coupled, and the universe was an opaque, glowing fluid. We can describe nuclear synthesis in the first minutes, and particle processes at even earlier fractions of a second. Each step relies on tested physics, but each step also pushes toward regimes we cannot recreate fully, even with the most powerful accelerators. As we approach the earliest instance, the uncertainties grow, and they grow in specific diagnosable ways. We infer conditions indirectly, through patterns in the CMB and the distribution of galaxies, and through how structures cluster over cosmic time. We rely on assumptions about the contents of the universe, like dark matter and dark energy, and on the validity of relativity at extreme energies. We confront open problems like the horizon problem and the flatness problem, which hint that the early universe may have undergone a special phase. Why do distant regions look so similar? And why is space so close to geometrically flat? Unless something set those conditions, that hint leads to inflation, a proposed period of accelerated expansion very early on, when the scale factor grew at an extraordinary rate. Inflation is not the Big Bang itself, but a mechanism that could set initial conditions for the hot Big Bang phase. It can explain why the universe looks so uniform across vast distances, and why space appears nearly flat because rapid expansion would dilute curvature and smooth gradients. It can also seed the tiny fluctuations we see in the CMB through quantum processes stretched to cosmic scales, turning microscopic uncertainty into macroscopic pattern. Inflation, if real, shifts the origin question rather than erasing it, and that shift is part of the drama. It asks what drove inflation, how it started, and whether it ended everywhere or only in our region. Some inflation models suggest a multiverse, where inflation continues in some regions and stops in others, producing bubble-like domains with different histories. That possibility raises new questions about what counts as an explanation and what counts as an untestable extension, especially when evidence may be indirect. Beyond inflation, other ideas challenge the notion of a single beginning, while still trying to respect the same observational pillars. Cyclic and bounce models propose that a prior phase preceded our expansion, perhaps a contracting universe that rebounded, avoiding a singularity. Some scenarios emerge from quantum gravity approaches, where space-time avoids singularities by modifying geometry at extreme density. These models aim to replace time begins with time continues through a transition, though they face their own observational hurdles and must still reproduce the CMB's precise patterns. There are also proposals where the universe is a quantum event, like tunneling from a metastable state, or arising from a wave function with specific boundary conditions. In those pictures, the cause is not a prior event, but a rule governing what histories are allowed and which are suppressed. The language of causation becomes the language of probability and constraint, which can feel alien but remains mathematically sharp. The question becomes whether the laws themselves can be explained, or whether they are the final bedrock, an answer that would be satisfying to some and unsettling to others. At every step, we will keep returning to the same discipline. What is measured? What is inferred? What is assumed? The mystery is not an excuse to accept any story that feels satisfying. It is a reason to be precise about what science can say and what it cannot yet say, while admitting that the edge of knowledge is a moving boundary. This chapter ends at the edge of the beginning, where evidence fades into extrapolation, and extrapolation fades into open theory. We have corrected the picture of a cosmic explosion and replaced it with expanding space-time, a quieter but deeper image. We have anchored the Big Bang in 3 observational pillars that make it more than a metaphor and more than a guess. We have also located the fracture line, where singularities and quantum gravity force new thinking, and where our best equations begin to speak in warnings. Now we follow the trail in the only direction science allows, from the evidence in the sky, to the earliest moments we can model, to inflation and its alternatives, and finally to the hardest question of all. If time and space emerged, what does it mean to ask what came before, and what would count as an answer that is more than words? Chapter 1 left us at a boundary where language strains to stay honest, because origins tempt us into metaphors that sound like explanations. This chapter stays on firmer ground by treating the universe like evidence, measurable, cross-checked, and stubbornly indifferent to our preferences. We cannot watch the beginning directly, because no camera can be placed before space-time as we know it, but we can test what a hot beginning predicts, and we can ask how well those predictions survive contact with data. We read the sky the way detectives read a scene, then we ask what the clues do not say, because silence can be as informative as testimony. To understand what we can ask, we start with what we can observe. The first clue is expansion, because expansion turns distance into history and makes the sky into a layered archive. Light from far galaxies left long ago, so looking outward is looking back across billions of years. In practice, every deep image is a time-lapse. Nearby galaxies are late frames and distant ones are early frames. If space has been stretching, then earlier space was smaller, and earlier matter was denser, and the temperature of radiation was higher. That simple chain, stretch, dilute, cool, sets the logic of the entire reconstruction. Astronomers see expansion through redshift, the systematic stretching of light's wavelength as it travels through an evolving cosmos. Spectral lines act like barcodes, letting us compare distant atoms to laboratory atoms with astonishing precision. Hydrogen, oxygen, calcium, and iron each stamp a recognizable pattern into a spectrum, and those patterns are not negotiable. The lines arrive shifted toward red, and the shift grows with distance in a way that is statistically clean. This pattern is not a one-off effect in one direction, but a sky-wide rule that holds in every survey field. Even when galaxies are locally moving in clusters, the large-scale trend remains, and it is that large-scale regularity that matters. In the 1920s, the rule became quantitative, then unavoidable, as telescopes and photographic plates turned faint smudges into measurable systems. Hubble measured galaxy distances using C-fired variable stars, whose period luminosity relation had been calibrated by Henrietta Leavitt's earlier work. He then compared those distances to redshifts, many measured by Vesto Slipher, and the correlation emerged with startling clarity. Lemaitre connected that relation to general relativity and an expanding metric, arguing that the mathematics already implied a dynamic universe. The Hubble, Lemaitre law says recession speed is proportional to distance on large scales, and it is a statement about the scale factor changing. It is not debris flying from a centre, and it does not privilege any location as the middle. That last point is easy to say and strangely hard to feel, because our instincts demand an explosion with an outward blast. Cosmological expansion is subtler. The distances between far apart, gravitationally unbound regions increase because the metric changes with time. Galaxies are not typically moving through space at extreme speeds like shrapnel, although they do have local motions. Instead, the map itself is being rescaled, and the rescaling is what the redshift primarily records. A useful mental image is a grid being stretched, with galaxies roughly pinned to the grid lines. The stretching is uniform on large scales, even though local regions can resist it through gravity. Redshift can be described with Doppler language, and for nearby galaxies that description is often adequate. But cosmology uses a deeper interpretation, because the dominant effect is not a single object's motion through a static arena. In an expanding universe, photons are stretched by the stretching of space, and their wavelengths lengthen as the scale factor grows. The relation is simple in form. The wavelength scales with the universe's size, so the redshift directly encodes the expansion during the photon's trip. That makes redshift a time machine, because it tags each photon with an earlier scale and an earlier cosmic environment. When we measure a galaxy's redshift, we're not just measuring how fast, but how long ago in a model-dependent testable way. Distances are the hard part, so cosmology builds a ladder of cross-checks rather than trusting any single rung. Nearby distances use geometry, including parallax, and then standard candles like Cepheids, whose intrinsic brightness can be inferred from their pulsation periods. Farther out, Type Ia supernovae serve as calibrated explosions because their peak luminosities can be standardized using light curve shapes and colors. Other indicators, surface brightness fluctuations, the Thule, Fisher relation, and gravitational lensing time delays, provide independent routes with different systematics. Large surveys map redshift and position for millions of galaxies, turning individual measurements into statistics that can be stress tested. The point is not one method, but convergence across methods, because agreement among imperfect tools is often the strongest kind of reliability. Once expansion is measured, the equations invite a dangerous move, because mathematics makes reversal feel effortless. Run the expansion backward and the scale factor shrinks, and the average density rises as volume falls. Matter density increases roughly as the inverse cube of the scale factor, while radiation density rises even faster because photon energy also blue shifts. Radiation temperature rises as wavelengths compress, and the same equations that describe cooling forward describe heating backward. In that backward movie, the universe becomes hotter, denser, and more uniform, and the familiar structures of today dissolve. Galaxies blur into gas, gas becomes plasma, and plasma becomes a seething bath of particles and light. This is not a claim that everything converges to a point in pre-existing space, as if the universe were a firework launched into emptiness. It is a claim that the metric describing distances changes with time, and that space is part of the dynamical system. When the scale factor approaches zero in simple models, densities diverge, and curvature invariance can blow up. That divergence is the famous singularity, which may be a real boundary or a sign of missing physics. Either way, expansion gives a direction to the investigation, because it ties present measurements to past conditions through a calculable chain. Even before we reach that boundary, the backward extrapolation becomes a laboratory of constraints. If the early universe was too lumpy, we would see stronger anisotropies in the relic radiation. If it expanded too fast or too slow, the light element abundances would shift in ways we can measure. If it contained exotic energy components at the wrong time, the pattern of acoustic peaks would be distorted. The remarkable fact is that multiple, independent relics agree on a consistent thermal history. That agreement does not prove the ultimate beginning, but it narrows the range of plausible stories. The second clue is the cosmic microwave background, the afterglow of that early heat, and it is among the most visually arresting pieces of evidence in all of science. If the early universe was a hot plasma, it should have been filled with thermal radiation, because charged particles scatter photons efficiently. As the universe expanded, that radiation should cool and stretch into microwaves, sliding down the electromagnetic spectrum like a fading ember. It should also arrive from all directions, because the early plasma filled all space within our observable region. The CMB is that prediction made visible, not as a photograph of a moment, but as a map of a surface in time. The CMB is measured as a nearly perfect blackbody spectrum at about 2.7 to 25 Kelvin, a temperature only a few degrees above absolute zero. A blackbody curve is not merely smooth, but mathematically specific, and it is the signature of matter and radiation once being in thermal equilibrium. Equilibrium erases many details of initial conditions, which is why the spectrum is so clean, and why it feels almost uncanny. The spectrum is not a vague glow, but a precise shape measured across frequencies, with deviations constrained to tiny levels. That precision is one reason the hot beginning model became the standard, because few astrophysical alternatives can mimic such an exact thermal relic. To appreciate what blackbody means, imagine tuning a radio dial across many bands and finding the same underlying curve everywhere, as if the universe itself were a calibrated instrument. The peak of the CMB spectrum sits in the microwave range today, but in the past it was hotter and peaked at shorter wavelengths. In the early universe, the same radiation would have looked like a bright, diffuse glow, more like the interior of a furnace than the night sky. Expansion did not create the photons, but it diluted and cooled them, preserving their thermal character while shifting their energy. The CMB is therefore both ancient and present, a relic that still fills the room we call space. The CMB also carries a timestamp because it comes from a specific transition in the universe's thermal chemistry. Early on, electrons and nuclei were separate, and photons scattered constantly off free charges. The universe was opaque, because light could not travel far without being deflected, absorbed, or re-emitted by the plasma. As expansion cooled the plasma, the average photon energy dropped below the ionization energy of hydrogen, often enough for neutral atoms to survive. Electrons bound to nuclei and formed neutral atoms in a process called recombination, and it happened about 380,000 years after the hot beginning. The name is slightly misleading. Electrons and protons were combining for the first time, but the physical effect is clear. The fog lifted. When photons stopped scattering freely, they decoupled from matter and streamed outward, carrying with them a record of the conditions at that moment. Those photons have been travelling ever since, cooling as space expanded, and their wavelengths have been stretched by roughly a factor of 1,000. We see them today as the CMB, arriving from a spherical shell of last scattering centred on us, because we observe along our past light cone. That shell is not an edge of the universe, but an observational horizon set by opacity and time. The CMB is a snapshot of the universe when it first became see-through, like the earliest frame in a cosmic film that can still be projected. Uniformity is the first shocking feature of that snapshot, and it is easy to miss because the maps are often shown in false colour. The CMB temperature is almost the same in every direction, so uniform that the raw sky looks nearly featureless. The deviations are tiny, at the level of about 1 part in 100,000, around 10 to the 5, and yet they are physically decisive. Those anisotropies are not noise, but the seeds of everything structured, the faint blueprint from which galaxies and clusters eventually emerged. They are the small initial wrinkles that gravity later amplified, and they are measured with a care that borders on obsessive because the signal is so subtle. Measuring those wrinkles required instruments that could see microkelvin differences while controlling for foreground contamination from our own galaxy. Cope first detected the black body spectrum with high confidence, establishing the thermal nature of the relic radiation beyond serious doubt. It then found the anisotropies, a discovery that turned a theoretical prediction into a mapped reality. WMAP mapped the anisotropies across the whole sky with improved resolution and stability, sharpening the acoustic peak structure in the power spectrum. Planck refined the map again, tightening constraints on cosmological parameters and measuring polarization with greater sensitivity. These missions did not just take pictures, they measured statistics of fluctuations, and they did so while modelling dust emission, synchrotron radiation, and instrumental noise. The key statistic is the angular power spectrum, which organises anisotropies by scale and turns a mottled sky into a quantitative fingerprint. Each multipole corresponds to a characteristic angular size, and the distribution of power across multipoles encodes early universe physics. Peaks and troughs reflect acoustic oscillations in the early plasma, where gravity tried to compress overdense regions and radiation pressure pushed back. That tug-of-war created sound waves, literal pressure waves in a coupled photon, baryon fluid, and those waves left an imprint in temperature and polarization. The peak pattern depends on matter density, baryon density, and geometry, and even the relative heights of peaks carry information about how much ordinary matter was present. In plain terms, the universe rang like a bell, and the CMB preserves the overtones. The CMB is also polarized, and that polarization adds another layer of evidence that is both technical and profound. Thomson, scattering at recombination produces a characteristic polarization pattern when the incoming radiation has a quadrupole anisotropy. By decomposing the polarization into E modes and B modes, cosmologists can separate different physical sources and improve parameter estimates. E modes are now measured with high precision, and they cross-correlate with temperature fluctuations in ways predicted by the same underlying model. B modes are harder, because gravitational lensing and galactic dust can mimic them, but the search continues because of what they might reveal. A primordial B-mode signal would hint at gravitational waves from an even earlier epoch, though the core point remains, the CMB is a precision relic, not poetic metaphor. There is also motion hidden in the CMB, and it shows up as a dipole anisotropy that is much larger than the intrinsic fluctuations. That dipole is interpreted as our motion relative to the CMB rest frame, a kind of cosmic reference defined by the relic radiation itself. Subtracting it reveals the delicate 10-5 pattern underneath, like removing a strong spotlight to see faint starlight. This separation is a reminder that cosmology is not done from nowhere, but from a moving platform inside the universe. Even so, after corrections, the same statistical pattern emerges, and it is consistent across instruments and analysis pipelines. The third clue is chemical, and it is older than stars because it comes from a time when there were no stars at all. If the early universe was hot and dense, nuclear reactions should have occurred briefly, not in stellar cores, but in the cosmic plasma itself. As the universe expanded, it cooled too fast for long-term fusion, and the density dropped too quickly to keep reactions going. That creates a narrow window in the first few minutes when light elements form, after which the universe becomes too cold and too dilute. Big Bang nucleosynthesis predicts specific abundances from that window, and those abundances are sensitive to the conditions at the time. It is a rare case where we can test minute old physics using atoms we can still measure today. The main product is helium-4, because it is the most stable light nucleus, and because neutrons, once they survive long enough, tend to end up bound in helium. BBN predicts that about a quarter of ordinary matter by mass becomes helium-4, a striking number given that hydrogen dominates by atom count. The rest remains mostly hydrogen, with trace amounts of deuterium, helium-3, and lithium-7, each produced through specific reaction pathways. These ratios depend on the expansion rate, which sets the timing, and on the baryon to photon ratio, which sets how readily nuclei can find each other. That makes primordial abundances a test of early conditions, not merely a catalogue of cosmic ingredients. The logic of the timing is almost cinematic. At very high temperatures, nuclei cannot hold together, because energetic photons break them apart as soon as they form. As the universe cools, there comes a moment when deuterium can survive without being immediately photodissociated, and that moment triggers a rapid chain toward helium. This deuterium bottleneck means that the onset of nucleosynthesis is delayed until conditions are just right. Meanwhile, free neutrons are unstable and decay with a half-life of about 10 minutes, so the clock is always ticking. The helium fraction therefore encodes a race between cooling, reaction rates, and neutron decay, and the result is a robust prediction. Helium is robust, but deuterium is the sensitive probe, and its fragility is exactly what makes it so valuable. Deuterium is easily destroyed in stars, so any deuterium we see today is a lower bound on its primordial amount. In the early universe, deuterium forms and then quickly fuses into helium if conditions allow, because higher densities make collisions more frequent. A higher baryon density makes fusion more efficient and leaves less deuterium behind, while a lower baryon density leaves more deuterium unburned. That is why deuterium acts as a baryometer, a way to weigh the amount of ordinary matter in the cosmos. It is a delicate chemical memory of the universe's first minutes. Observations target environments that preserve early chemistry, because most places have been processed by generations of stars. Astronomers measure deuterium in distant, nearly pristine gas clouds, seen in absorption against quasars, where the light passes through intervening hydrogen and leaves a spectral imprint. In those spectra, deuterium's lines are slightly shifted relative to hydrogen's, and separating them requires high resolution and careful modelling of velocity structure. They estimate primordial helium from low metallicity regions, such as certain dwarf galaxies and ionized nebulae, where stellar processing is minimal and heavy elements are scarce. The results broadly match BBN predictions when combined with CMB-inferred baryon density, and the match is not just qualitative. The agreement links minutes-old physics to 380,000-year physics, tying nuclear reaction networks to microwave maps. Lithium is the awkward part, and it matters because it shows the method's honesty rather than its perfection. BBN predicts a lithium abundance that does not perfectly match what is inferred from old, metal-poor stars, where lithium should preserve an early signature. This lithium problem could reflect stellar depletion, where lithium is transported into hotter layers and destroyed, or it could reflect systematic errors in atmospheric modelling and line formation. It could also hint at new physics that subtly alters reaction rates or particle content during nucleosynthesis, though such fixes are constrained by the success elsewhere. The tension is real, but it does not erase the broader success, because the helium and deuterium concordance is strong. It instead marks where the model is tested hard enough to reveal cracks, which is often how progress announces itself. These 3 clues connect into one story with internal consistency, and the consistency is the point. Expansion sets the overall cooling history and gives a way to run time backward in a controlled, equation-based way. The CMB shows a hot, thermal, nearly uniform early universe, with tiny fluctuations that behave like acoustic relics. BBN shows that the early universe once reached nuclear temperatures for a short time, producing light elements in predictable ratios. Each clue is measured differently, and each points to the same hot, dense phase, even though the systematics and instruments are unrelated. In detective terms, the witnesses do not appear to have coordinated their stories. A 4th clue is structure, because the universe is not only smooth, and the present-day cosmos is visually dominated by clumping. Galaxies cluster into filaments and walls, and clusters sit at the nodes, while vast voids open like dark basins between them. In wide-field surveys, this web is not a metaphor but a pattern that can be plotted, measured, and simulated. Yet this structure did not exist in the early plasma, because the CMB is too smooth to hide large clumps. So structure must have grown from small initial perturbations amplified over time by gravity. The question becomes whether the initial perturbations match what the CMB shows, not only in amplitude but in statistical character. Gravity provides the growth mechanism, but growth is slow in an expanding universe, because expansion acts like a kind of friction against collapse. Overdensities attract more matter, becoming denser over time, while underdensities lose matter and become voids that expand faster than average. The competition between attraction and expansion can be written in growth equations, and those equations depend on the contents of the universe. Dark matter matters here, because it can start clumping before recombination, being largely unaffected by radiation pressure. Baryons were coupled to photons and could not collapse efficiently until decoupling, so they fell into the dark matter, potential wells later. This division of labour, dark matter first, baryons later, helps explain how small early fluctuations can become large present structures. The CMB anisotropies provide the initial conditions for this growth, and their amplitude is about 10 Promorphive, which seems too small at first glance. But given billions of years, and given that dark matter begins clustering early, those small perturbations can grow into today's structure. Simulations that start from CMB consistent fluctuations reproduce large-scale clustering patterns, including the filamentary network and the distribution of cluster masses. They also reproduce statistical measures like the 2-point correlation function and the matter-power spectrum across wide scales. That match is not perfect in every detail, because baryonic feedback from stars and black holes complicates small scales. Still, the broad success is hard to dismiss, because it connects the faint microwave wrinkles to the luminous architecture of galaxies. Large-scale structure also preserves a specific early universe ruler, and it comes from the same physics that shapes the CMB peaks. Before recombination, baryons and photons formed a coupled fluid with pressure waves, and those waves propagated outward from overdense regions. When photons decoupled, the waves effectively froze, leaving a slight enhancement of baryonic matter at a characteristic radius. That radius is set by how far sound could travel before decoupling, and it is called the sound horizon. The imprint is called baryon acoustic oscillations, and it is subtle but measurable across enormous volumes. In effect, the universe stamped a preferred separation scale into the distribution of matter. BAO is measured in galaxy surveys as a bump in the correlation function, a small excess probability of finding galaxy pairs separated by the sound horizon scale. It is also measured in the power spectrum as a series of wiggles, a harmonic pattern that echoes the early oscillations. The scale is set by well-understood early universe physics, including the baryon density and the expansion rate before recombination. Because the scale is known, BAO acts as a standard ruler, letting us infer distances from angles and redshifts. It helps map how expansion changed over cosmic time, including the late-time acceleration inferred from supernovae. The method is powerful because it relies on a geometric imprint rather than a complex astrophysical luminosity model. BAO links late-time geometry to early-time plasma physics, and that linkage is one of the chapter's quiet triumphs. When BAO and CMB measurements agree on the sound horizon and on cosmological parameters, the model gains credibility because two very different epochs are speaking the same language. When they disagree, the model is forced to evolve because the ruler cannot easily be redefined without consequences elsewhere. Current data show broad consistency, with active debates about the Hubble constant and related tensions that may signal subtle systematics or new ingredients. Those debates are not failures of the detective story, but signs that the evidence is precise enough to be uncomfortable. Precision is where mysteries sharpen, because small discrepancies can point toward big revisions. At this point, the Big Bang is not a slogan, but a tested framework with multiple independent pillars. It says the universe expanded from a hotter, denser state, and that cooling and dilution shaped everything that followed. It predicts a relic radiation field with a blackbody spectrum and specific anisotropies, and those predictions are borne out in detail. It predicts light element abundances from a brief nuclear epoch, and those abundances largely match what we infer from carefully chosen environments. It predicts that structure grows from tiny initial fluctuations and preserves acoustic imprints, and surveys find those imprints in the distribution of galaxies. The framework is not a single argument, but a network of constraints that reinforce one another. Here we meet the boundary of evidence and the boundary of theory, and the boundary is not a wall so much as a change in footing. The evidence supports a hot beginning, but it does not automatically explain why that beginning had the properties it did. The model needs initial conditions to run, even when the equations are correct, and those conditions are not derived from the model itself. It needs a near-uniform early state with small perturbations of a particular type, close to Gaussian and nearly scale invariant. It needs an overall expansion history that starts in a special regime, because small deviations early can grow into large differences later. The deeper question is not whether the hot phase happened, but why it was so orderly. Running the equations backwards sharpens this tension, because extrapolation becomes more daring as we approach earlier times. The closer we push toward the earliest moments, the more the model relies on physics tested indirectly rather than directly. We trust general relativity and known particle physics within tested domains, and we have good reasons for that trust. But at extreme densities and energies we expect new physics, because quantum effects and unknown fields may become unavoidable. The singularity in simple solutions is a warning that the description is incomplete, not a triumphal endpoint. It is a signpost that says, in effect, your map ends here. The CMB's uniformity is itself a clue that becomes a puzzle, because it is too good for the simplest story. Regions of the CMB sky far apart were not in causal contact in the simplest hot Big Bang picture, because light would not have had time to travel between them before recombination. Yet their temperatures matched a high precision, as if they had been in thermal communication. This is the horizon problem, and it suggests that something set uniform conditions across a larger region than naive causality allows. The near flatness of space is another puzzle, because flatness is unstable under ordinary evolution and would require extraordinary fine-tuning at early times. Why should curvature be so close to zero, unless some mechanism drove it there? One response is to propose an early phase that prepares the hot Big Bang, and inflation is the leading idea. Inflation is an era of accelerated expansion before the plasma epoch, during which the scale factor grows extremely rapidly. Inflation can stretch a small, causally connected patch into the entire observable universe, turning local uniformity into global uniformity. It can drive curvature toward near zero, smoothing out gradients and diluting unwanted relics that might otherwise dominate. It can also generate quantum fluctuations that become the seed seen in the CMB, turning microscopic uncertainty into macroscopic structure. In this way, inflation is both a smoothing mechanism and a perturbation generator, a rare combination. Inflation is not yet the focus of this chapter, but it frames the coming turn because it shows how evidence can point beyond itself. Even if inflation happened, it raises deeper questions about what started inflation and why it ended. Because an accelerated phase must be triggered and then shut off. It replaces one set of initial conditions with another set, often involving a field and a potential that must be specified. It can be predictive, but it can also be flexible, depending on the model, and flexibility can blur the line between explanation and accommodation. The origin question shifts rather than disappears, and that shift is part of the story we are building. So we separate what the evidence establishes from what it leaves open, because clarity here prevents both overreach and needless skepticism. The evidence establishes a hot, dense early phase with specific measurable relics, and it establishes that the universe's history can be reconstructed with surprising precision. It does not establish a unique story for the earliest boundary, or whether there is a boundary at all, because multiple mechanisms can lead to similar late-time relics. It does not tell us what selects the initial state, or whether selection is the right concept in a context where time itself may be part of what is being explained. In a sense, the evidence draws a circle around what must be true, while leaving the centre intriguingly empty. This is where the central question returns with more force, because the success of the reconstruction makes the missing piece more conspicuous. If the Big Bang marks the beginning of our observable universe, what can science say about the cause or conditions that led to it? Evidence can tell us what the early universe was like after a certain time, and it can constrain what could have happened earlier by limiting what would spoil the relics. But it may not translate cleanly into a cause, because causation assumes a time order, and time is part of the system under investigation. When we ask what caused the beginning, we may be asking a question whose grammar is older than the physics. Even the word initial can be misleading, because it smuggles in a picture of a first moment sitting on a timeline like a starting gun. In mathematics, we set initial conditions to solve differential equations, and we do so because we already assume time as a parameter. In cosmology, those conditions might be replaced by boundary conditions, or by a quantum state, or by a deeper law that does not look like a starting snapshot. The question becomes whether the universe began in time, or whether time is emergent from something more fundamental. The evidence does not settle that, but it tells us where the next questions must live, and it tells us what any deeper theory must reproduce. We end this chapter with a paradoxical confidence, because the Big Bang model is strong in exactly the way that makes the mystery sharper. The model is strong because it explains multiple datasets with one coherent thermal history, and because it survives tests that were not designed to flatter it. That strength makes the origin puzzle more pointed, because the model's success demands an explanation for its starting point and its unusual simplicity. The clues point back to a hot beginning, but they also point to a missing chapter, a preface that the data only hint at. In the next step, we follow the trail toward the mechanisms that might set the initial state, and toward the possibility that the word cause must be rewritten, carefully and with evidence in hand. Rewind the universe far enough and you reach a moment so hot, so dense, so utterly alien that the matter you're made of didn't exist yet. No atoms, no protons, not even the particles inside them behaving the way they do now. And in that first sliver of a second, physicists found something they still can't fully explain, a state of matter so strange it behaves more like a perfect liquid than anything in the cosmos today, hiding a fingerprint that quietly shaped every star, every planet, and every atom in your body. What happened in those first fractions of a second? You won't believe how close we came to a universe with no matter at all. Stay with us, because this is where the known laws of physics start to blur. Visually, imagine the universe not as a place but as a state of matter. The background is not black space with stars, but a glowing opaque fog of particles, bright enough to hide any distance. Photons scatter constantly, and every charged particle is jostled by electromagnetic forces as if the cosmos were a boiling liquid. The entire observable region behaves like a single furnace whose thermostat is time, cooling not because heat escapes, but because space itself expands. When we say rewind, we are really tracking how the scale factor shrinks. As the scale factor decreases, wavelengths compress, and the average energy per particle rises, because radiation is stretched and squeezed by geometry. In a radiation-dominated universe, temperature scales roughly as the inverse of the scale factor, aside from brief episodes when species annihilate. That simple relation lets us convert an abstract expansion history into a thermal history we can calculate, and it turns time into something we can label with energy. At minutes old, the universe is already cool enough for nuclei to survive without being instantly torn apart. Big Bang nucleosynthesis runs from roughly 1 second to a few minutes, building deuterium and helium from protons and neutrons. The key is not just that fusion occurs, but that it occurs briefly, then stops, because the density drops too fast. Expansion lowers density and temperature so quickly that nuclear reactions freeze out before heavier elements can form, leaving a chemical fingerprint that later stars will inherit. The outcome depends on the expansion rate, the baryon density, and the number of light particle species. Expansion rate controls how long reactions have to proceed before the universe dilutes, like a timer that cannot be paused. Baryon density controls how often protons and neutrons collide, because more baryons mean more targets per cubic meter, even in a rapidly thinning plasma. The number of light species matters because every relativistic particle contributes to the total energy density, and energy density sets the Hubble rate through gravity. The famous result is deceptively simple. A universe that begins hot and expands predicts a primordial mixture. Hydrogen dominates, helium-4 is substantial, and trace amounts of deuterium and helium-3 remain, each sensitive to slightly different microphysics. Lithium appears too, though its observed abundance carries tensions that remind us the early universe still keeps secrets. Even here, where the model works impressively, nature leaves small discrepancies that sharpen our questions, as if the data were nudging us toward missing details. Before nuclei form, neutrinos slip away, and the universe becomes quieter in an invisible channel. Around 1 second, weak interactions can no longer keep neutrinos in thermal contact with the plasma, so neutrinos decouple and free stream through everything. The weak force is still present, but reaction rates fall below the expansion rate, and the universe outruns its own ability to equilibrate. In practice, the universe expands faster than neutrinos can continue exchanging energy with electrons and positrons, so the neutrinos keep what they have. Neutrino decoupling is subtle because it is not a single on-off switch. It is a gradual process in which scattering becomes rare, and the neutrino distribution begins to drift away from perfect equilibrium, with small distortions that careful calculations track. Yet the basic picture holds. After decoupling, neutrinos travel almost unimpeded, carrying away a fossil record of the early thermal state. Their energy density still affects expansion, so neutrino physics leaves an imprint even when neutrinos become nearly invisible, shaping timing and abundances indirectly. If you could see neutrinos, the scene would change dramatically. The universe would look like a storm of ghostly particles streaming through everything, crossing the frame in straight lines that ignore the glowing plasma. They would pass through the densest furnace as if it were mist because their interactions are so feeble at these energies. That is why neutrinos are both frustrating and precious, hard to detect yet deeply informative, because they preserve what photons cannot. A few seconds later, electrons and positrons annihilate as the temperature drops below their rest mass. Most pairs disappear into photons, heating the photon bath relative to the neutrino background, because photons remain tightly coupled to charged particles. This is an entropy transfer, and it is one of the cleanest thermodynamic episodes in the early timeline, almost like a controlled experiment. The universe conserves entropy in co-moving volume, but it redistributes that entropy among the species still coupled, and the bookkeeping is statistical rather than mysterious. The result is a measurable ratio. Photons end up warmer than neutrinos by a factor set by statistical physics, because photons receive the annihilation energy, while neutrinos mostly do not. That simple heating episode helps set the photon to neutrino temperature ratio we infer today, even though we cannot yet directly map the neutrino background. It is also why the cosmic microwave background is not merely leftover light. It is a calibrated relic with a known thermal history, carrying a temperature that is meaningful. Now we push earlier than a second into the microsecond regime where matter itself has a different identity. At about 10 microseconds, the universe is hot enough that quarks and gluons are not confined inside protons and neutrons. Matter exists as quark, gluon plasma, a strongly interacting fluid where hadrons cannot yet form stable identities because the medium itself disrupts binding. Instead of discrete particles bouncing like billiard balls, the dominant behavior resembles a near-perfect liquid, with collective flow and rapid thermalization. This is quantum chromodynamics in its most dramatic regime. At high temperature, the strong force changes character because of asymptotic freedom, a discovery that reshaped 20th century particle theory. Quarks interact more weakly at very short distances, yet the medium is so dense that collective effects dominate, and individual trajectories lose meaning. The plasma supports waves, screening, and rapid equilibration, features more like condensed matter than like empty space, even though it is built from fundamental fields. As the universe cools through roughly 150 to 200 MeV in temperature, confinement turns on. Quarks bind into hadrons in the quark, hadron transition, and the particle zoo reorganizes into protons, neutrons, pions, and their short-lived relatives. The transition is not necessarily a sharp first-order phase change in the simplest picture, and lattice calculations suggest a smooth crossover for our conditions. For the conditions of our universe, it likely behaves as a smooth crossover, where properties change quickly but continuously, without a single dramatic boundary. That distinction matters because phase transitions can leave relics. A violent first-order transition could generate bubbles, shocks, and out-of-equilibrium pockets, which might seed in homogeneities or produce gravitational wave backgrounds. A crossover is gentler, though still consequential for how densities and reaction rates evolve, and for how baryons become the long-lived carriers of baryon number. Either way, the moment marks a redefinition of what matter means, because the universe begins to prefer bound states over free quarks. This is not a distant fantasy, because heavy ion collisions briefly recreate similar conditions on Earth. At facilities like RHIC and the LHC, nuclei slam together at enormous energies, and for an instant the collision zone behaves like quark, gluon plasma, expanding and cooling in miniature. Detectors infer its properties from jets, flow patterns, and particle yields, translating debris into a fluid story. The early universe did not happen in a lab, but the lab offers a controlled hint about its physics, and it anchors our intuition in data. Imagine the visual here as a slow morph. The screen begins as a shimmering incandescent fluid with no stable shapes, like a bright ocean with ripples made of fields. Then, as temperature drops, islands of identity emerge, protons and neutrons becoming recognizable, like droplets condensing out of vapor. The universe is still opaque, still violent, yet it is beginning to acquire the building blocks chemistry will later rely on, and the future suddenly has ingredients. Keep rewinding and the symmetry of the forces changes again, and the language of separate forces becomes misleading. Above about 100 GeV, the electromagnetic and weak forces merge into a single electro-weak interaction, described by a unified gauge structure. The Higgs field no longer selects a preferred direction in field space, so particles that are massive today behave as effectively massless, because the symmetry is restored. In that regime, the difference between a photon and a weak boson is not the difference we know now, and the familiar categories are not yet defined. Historically, this unification was not guessed from philosophy alone. It was built from precise experiments and a theoretical structure that predicted new particles, including neutral currents and heavy vector bosons. The discovery of the W and Z bosons in the 1980s confirmed the electroweak theory's central claims, and it turned abstract symmetry into measured mass. Decades later, the Higgs boson was observed, completing the simplest version of the mechanism that gives masses to fundamental particles and closing a long arc of prediction. When we talk about the electroweak era, we're leaning on that hard-won chain of evidence, not on aesthetic preference. In this electroweak era, the universe is a dense soup of leptons, quarks, gauge bosons, and Higgs excitations. Reaction rates are enormous, so equilibrium holds for many species, and the plasma forgets many details of earlier conditions because collisions erase memory. Collisions are so frequent that distributions relax toward thermal forms quickly, and chemical potentials remain small. Yet some details can survive, because not everything is erased by equilibrium, and conserved quantities still constrain what can happen. One surviving detail is the matter-antimatter asymmetry, which is a small imbalance with enormous consequences. The observable universe contains far more matter than antimatter, and the imbalance must have been set early, when reactions could still violate certain symmetries. If matter and antimatter had been produced in exact equality, nearly everything would annihilate into radiation, leaving a universe of photons and neutrinos. The fact that anything remains, enough to form galaxies, planets, and us, means the early universe favoured matter by a tiny fraction, roughly 1 extra baryon per billion photons. Baryogenesis is a placeholder name for mechanisms that satisfy known conditions, but the specific pathway remains uncertain. We know the broad requirements: baryon number violation, C and CP violation, and departure from thermal equilibrium, so that an imbalance can be generated and preserved. Those criteria, articulated clearly in the 20th century, are a kind of checklist for any successful explanation, and they constrain our imagination. Yet the universe does not hand us the recipe, and our experiments have not pinned down the necessary ingredients, leaving the narrative open at a crucial step. This uncertainty is not a failure of the Hot Big Bang model, but a sign of its ambition. The model is strong enough to tell us what must have happened, even when it cannot tell us exactly how, and that is a rare kind of scientific power. It is also a reminder that early is not only a time label, It is a regime where new symmetries, new particles, or new interactions might become relevant, and where the familiar inventory may not be complete. Even in a compressed timeline, the pattern is consistent and mathematically disciplined. As temperature rises, more particle species become active, and the effective number of degrees of freedom increases, changing the heat capacity of the cosmos. That changes how energy density scales and how fast the universe expands at a given temperature, because gravity responds to the total. When species become non-relativistic and annihilate or decay, they dump entropy into the remaining plasma, and the temperature does not fall as simply as geometry alone would suggest. The universe is not only cooling, it is continually rearranging who carries its heat and who gets left behind. To understand what we can ask, we start with what we can calculate. The Friedmann equations connect expansion rate to energy density, and particle physics connects energy density to temperature and species content, using well-tested statistical mechanics. This bridge lets us map time to temperature even when we cannot directly observe the plasma, because the equations are local and the assumptions are explicit. It is a remarkable situation. We cannot see the first microsecond, yet we can still compute its rough conditions, and we can check consistency through later relics. In a radiation-dominated era, the expansion rate scales with the square of temperature, up to factors that count particle species. That means a small change in temperature corresponds to a dramatic change in time, because the clock runs differently at higher energies. The first second contains an enormous range of energies and transitions, stacked tightly together like pages pressed into a thin book. When we say fractions of a second, we are not talking about a gentle countdown. We're talking about a cascade of physical regimes, each with its own effective description. But the bridge has a limit, and the limit is not a lack of imagination. It is a boundary where two successful theories demand to be used together, yet refuse to fully agree, because they encode reality in different languages. General relativity treats space-time as smooth and classical, while quantum theory treats fields as uncertain and discrete in their excitations, with probabilities built in. Each theory is extraordinarily accurate in its domain, and both are used daily in modern technology, from GPS to semiconductors. Yet at the earliest times their domains overlap, and the overlap is where our confidence thins. The closer we approach the earliest instance, the more gravity matters. Density rises as we rewind, so curvature rises, and the gravitational field becomes intense enough that quantum effects cannot be ignored, even in principle. Gravity is normally weak in particle experiments because energies are modest compared to the Planck scale, so it can be neglected safely. In the early universe, energy densities become so high that gravity stops being a background and becomes a participant, shaping the quantum environment itself. At some point, the classical geometry of spacetime should fluctuate, because energy and time are linked by quantum uncertainty. In ordinary quantum field theory, particles fluctuate on a fixed stage, and the metric is treated as a stable arena. Near the beginning, the stage itself should shimmer, because the metric is sourced by energy that cannot be perfectly definite, and uncertainty becomes geometric. The question becomes unsettling. What does before mean if time is part of the fluctuating system, rather than the container for it? This is where the Planck scale enters as a signpost, not as a guaranteed physical wall. The Planck time is about 5.30 × 10^44 seconds, and it marks when our usual extrapolation becomes unreliable, because quantum gravity correction should be large. The Planck length is about 1.62 × 10^35 meters, and it marks a scale where spacetime itself may not behave as a continuous manifold, at least not in the way relativity assumes. These numbers are unimaginably small, and that is precisely why they matter, because they sit where our best tools collide. Visually, the timeline compresses until it almost becomes a single bright line. Labels that once had room, microseconds, nanoseconds, picoseconds, pile up and overlap, and the screen feels crowded with vanishing intervals. The narration slows, because the concepts become delicate, and because certainty is no longer automatic. We are approaching a boundary defined not by observation, but by consistency, and consistency is a stern judge. These numbers are not arbitrary. They are built from the speed of light, Planck's constant, and Newton's gravitational constant, and they indicate where quantum mechanics and gravity have equal weight, like two forces meeting at a balance point. At those energies, treating gravity as a small correction fails because gravity becomes as strong as the other interactions, and perturbation theory breaks down. The Planck scale is where our usual approximation methods lose their footing, and where the familiar separation between geometry and matter may dissolve. When people say we need quantum gravity, they mean something specific and technically demanding. We need a framework where space-time geometry can be in quantum superposition, and where gravitational interactions are consistent with quantum principles, including unitarity and well-defined observables. We need predictions that reduce to general relativity at low energies and to quantum field theory where gravity is negligible, so the old successes remain intact. Without that, the earliest era is not merely unknown, it is undefined within our current language, because the terms themselves lose operational meaning. Here we meet the boundary of evidence and the boundary of theory. Evidence anchors the hot history back to minutes and seconds, and particle physics supports the microsecond and electro-weak extrapolations because the same interactions are tested elsewhere. But at the Planck boundary, the equations stop being trustworthy guides, and extrapolation becomes a kind of educated poetry. We can still write symbols on a page, yet we can no longer claim they describe reality with tested reliability, and that difference matters. This is the moment where the word singularity enters, and it must be handled carefully. In general relativity, a singularity is not primarily a point of infinite density in a literal physical sense. It is a statement about geodesic incompleteness, meaning some paths in spacetime cannot be extended to arbitrary values of their parameters, even though the equations ask them to. The mathematics is precise, even if the imagery is often misleading, and the precision is what makes the warning sharp. Geodesic incompleteness is a technical way to say the classical description ends. A freely falling observer's world line can reach an edge in finite proper time, and the theory offers no continuation beyond it, as if the map simply stops. That is not a cinematic object. It is a warning that the model has been pushed beyond its domain, and that the coordinates have run out of meaning. The singularity is less like a thing, and more like a missing chapter, where the narrative demands a new grammar. In many simple cosmological solutions, running the equations backward drives the scale factor towards zero. Curvature invariants can diverge, and densities become unbounded within the classical model, because nothing in the equations prevents the runaway. The singularity is then a mathematical endpoint, not necessarily a physical event that truly occurred, and not necessarily a place where infinite is realized. It is what the equations say when asked a question they were not built to answer, and the answer is a refusal. Physics has learned to distrust infinities as final answers, and that distrust is earned by history. Infinities often signal that a theory is being used outside its range, like fluid equations used beyond the scale of molecules, where the continuum assumption fails. Classical electromagnetism predicted catastrophic behavior in the ultraviolet, until quantum theory repaired it, and renormalization taught us how to handle divergences properly. The singularity problem is therefore a demand for new physics, not a proof that nature contains an actual infinite point, and the difference is more than semantics. This distinction matters for the central question because it changes what cause can mean. If the Big Bang marks the beginning of our observable universe, what can science say about the cause or conditions that led to it, without smuggling in assumptions about time? If the classical model breaks at the singularity, then the singularity cannot be the cause, because it is not a physical mechanism, only a boundary of description. A boundary in a model is not automatically a boundary in nature, and the universe is not obligated to respect our equations. So we reframe what the Big Bang is in this chapter's narrow sense. The hot Big Bang is the well-modelled thermal expansion after some earliest cutoff where our equations still work, and where the plasma description remains meaningful. The singularity is what appears when we extrapolate beyond that cutoff using classical gravity alone, ignoring quantum back reaction. In this framing, the Big Bang is not a single instant we can point to. It is an era, hot, dense, rapidly evolving, whose earliest moments may require new concepts, and perhaps a new notion of time. Now the narrative tension rises, because the timeline becomes both clearer and more fragile. We can list eras in accessible steps, but each step rests on assumptions about which laws remain valid and about which particles exist. The closer we get to the first fraction of a second, the more those assumptions become the story, because the evidence becomes indirect. The universe becomes a laboratory, but it is a laboratory we cannot enter, and the instruments are relics. At around 10 to raise us to 12 seconds, electroweak symmetry breaking occurs as the Higgs field takes on a non-zero vacuum expectation value. Particles acquire mass through their interactions with the Higgs field, and the weak force becomes short-ranged, changing reaction rates across the plasma. The exact nature of this transition depends on details that could connect to baryogenesis, including how strongly it departs from equilibrium. If the transition was strongly first-order, it could provide out-of-equilibrium conditions, with expanding bubbles of the new phase. If it is a smooth crossover, the universe must rely on other mechanisms and the mystery shifts elsewhere. At around 10^6 seconds, the quark, gluon plasma cools into hadrons. Protons and neutrons become meaningful, long-lived carriers of baryon number, and the universe's inventory simplifies into familiar building blocks. Their emergence is not merely a naming convention, because stable bound states change the reaction network, and they change what survives cooling. Once baryons exist, the universe can later build nuclei, and much later, still it can build atoms, and later still it can build chemistry. Later, at around 1 second, neutrinos decouple, and the weak interactions freeze out, setting the neutron-to-proton ratio. That ratio is crucial because neutrons are slightly heavier than protons, so equilibrium gradually favours protons as the temperature drops. As the universe cools, equilibrium favours protons, yet weak reactions keep converting one into the other until they slow, and the ratio locks in. After freeze-out, free neutrons begin to decay, and the clock starts ticking toward nucleosynthesis, with every second quietly reducing the neutron supply. At around a few minutes, nucleosynthesis locks many neutrons into helium-4. The remaining protons become the hydrogen that will later fuel stars, and the universe's first stable nuclei set a baseline for all later astrophysics. This chain links particle physics to chemistry, and it is one reason the Hot Big Bang is more than a story. It is a predictive framework that connects microphysical constants to the cosmic inventory, and it invites us to ask what would change if those constants were slightly different. The visuals here can become almost tactile. Show a cooling glow shifting from white to orange as the universe expands, with the fog thinning but never clearing. Overlay simple icons, quarks, then protons, then nuclei, appearing like milestones on a narrowing road, each one timed by temperature. Each milestone is a change in what can exist without being destroyed by heat, and each one is a constraint that funnels the future. Yet even this clean chain leaves puzzles that the vanilla model does not answer, and those puzzles are not minor. The first puzzle is the horizon problem, which is really a problem about causal contact and about how fast information can travel. Distant regions of the cosmic microwave background have nearly identical temperatures, even though they should not have equilibrated in the simplest timeline, given the finite speed of light. The issue is not that the universe is uniform, but that it is uniform beyond what light-speed communication appears to allow, and that uniformity is measured with precision. To picture the horizon problem, imagine two distant patches of the CMB sky. In the standard Hot Big Bang without an earlier mechanism, those patches were never close enough, long enough to share heat, because the horizon grows too slowly. They are like two rooms that were never connected by a hallway, yet somehow have the same temperature, down to tiny fluctuations. Why should their thermal histories match so precisely when their past light cones barely overlap? The question is not philosophical, it is quantitative, and it points to missing early dynamics. The second puzzle is the flatness problem, which is a problem about sensitivity to initial conditions. Spatial curvature evolves in a way that makes near flatness unstable under ordinary expansion, because matter and radiation dilute differently than curvature terms. In the equations, any small deviation from perfect flatness tends to grow in relative importance over time in a decelerating universe, making today's near flatness surprising. The observed near-flat geometry implies extraordinary fine-tuning in the early universe, unless some mechanism drives curvature towards zero, and does so robustly. Flatness can sound abstract, so translate it into a visual. Imagine balancing a pencil on its tip, and then rewinding time to ask how perfectly it must have been placed, with smaller and smaller tolerances. The earlier you rewind, the more impossible the balance looks without a stabilizing effect, because tiny errors would have toppled it long ago. In cosmology, that stabilizing effect would be a dynamical process, not a careful hand, and the equations demand something that acts like one. The third puzzle is the monopole problem, which is a problem about unwanted relics. Many grand unified theories predict heavy magnetic monopoles or similar topological defects in the early universe, produced when symmetries break in certain ways. If produced abundantly, such relics would dominate the mass density today, and they would be hard to miss, yet we do not see them. The absence is itself a clue, because it suggests either the theories are wrong in detail, or the early universe diluted the relics, hiding them in the vastness. These problems do not refute the hot Big Bang's later successes. They show that the hot phase needs an earlier prelude that sets initial conditions in a special way, before the thermal story begins. They also foreshadow why the question of cause may not be answered by simply rewinding the same equations, because the equations may start after the crucial setup. The hot Big Bang is a middle chapter that begins after something has already arranged the stage, and the stage looks suspiciously prepared. The horizon problem hints that the early universe was once smaller in causal terms than the observable patch we see. The flatness problem hints that curvature was dynamically suppressed, or never had a chance to grow, as if the universe were driven toward a special trajectory. The monopole problem hints that relics were diluted or never produced in the expected way, despite theoretical expectations. These hints point in the same direction, as if three different measurements are tracing the outline of one missing event, and the outline is hard to ignore. A single idea addresses all three in one move, and that idea is inflation. Inflation proposes a brief period of accelerated expansion before the hot radiation-dominated era, driven by an energy component with unusual pressure. It stretches a tiny, causally connected region into a vast domain, smoothing gradients and diluting curvature and relics, while preserving quantum fluctuations. It is a bold proposal, yet it is also economical, because it solves multiple problems with one dynamical episode, and it does so with calculable signatures. The key feature is acceleration. In ordinary expansion, distances grow, but causal horizons also grow in a particular way, so contact gradually increases. During inflation, the scale factor grows so rapidly that regions once in contact are carried far apart, and the horizon behavior reverses in the relevant sense. The universe becomes flatter because curvature is stretched away, like wrinkles pulled out of fabric, until the surface looks nearly perfect. Any unwanted relics become rare because their number density is diluted by an enormous volume increase, turning abundance into near absence. Inflation also offers a mechanism for the tiny fluctuations we later observe. Quantum fluctuations in fields during inflation can be stretched to cosmic scales, becoming the seeds of structure, and their statistics become a diagnostic. The CMB's nearly scale-invariant spectrum then becomes a clue about the inflationary dynamics and about how the accelerated phase unfolded. In this picture, galaxies begin as amplified quantum noise, an idea that is both unsettling and elegant, because it ties the largest structures to the smallest uncertainties. Visually, inflation is the moment the film seems to jump. A tiny patch expands so quickly that it fills the frame, and the texture smooths out as if ironed flat, leaving only faint ripples. Then, as inflation ends, the energy stored in the inflationary field is converted into particles and radiation, and the screen floods with a renewed glow. The universe reheats, returning to the hot, dense plasma we have been tracking with temperature, and the familiar thermal timeline begins again. But inflation is not a simple ending to the origin question, because it introduces its own beginning. If inflation happened, it becomes the new earliest chapter we can model, and it demands its own trigger, its own initial conditions, and its own explanation. We must ask what field drove inflation, what set its initial state, and what caused it to end and reheat the universe, without fine-tuning that merely moves the mystery. The solution to one set of puzzles becomes the doorway to deeper ones, and the doorway opens onto unfamiliar ground. This is where the central question transforms rather than disappears. The question shifts from what caused the Big Bang to what set off inflation, and what came before inflation if before is meaningful. The cause of the hot Big Bang may be the end of inflation, but the cause of inflation remains open, and it may be tied to quantum gravity. Even the word cause becomes delicate when time itself may be emergent, or when classical time loses definition. At the Planck boundary, even inflation may require quantum gravity to begin. Some models place inflation below the Planck scale and treat gravity classically, but the initial conditions may still trace back to a regime where space-time is quantum, and where initial is a tricky word. The wall of the Planck era remains, even if inflation moves the starting line, because the ultimate origin still points toward the same unresolved overlap. We can shift the frontier, but we cannot pretend it is gone, and the blur returns at the edge. So we end this chapter with two kinds of honesty, one triumphant and one restrained. We can describe the early universe from minutes back to microseconds, with a temperature-driven timeline tied to known physics, and we can test pieces of it through relics and laboratory analogues. We cannot reliably describe the Planck era, because we lack a tested quantum theory of gravity, and because our best frameworks do not yet merge. Our confidence fades not because we stop thinking, but because our tools stop agreeing, and disagreement is where mystery lives. The singularity is not a proven event in the world. It is a signpost that classical general relativity has been pushed past its domain, and that the concept of time may be part of the unknown, not the backdrop. The horizon, flatness, and monopole problems sharpen the need for new early universe physics, because they are measured tensions, not aesthetic complaints. They are the clues that the Hot Big Bang is not the whole story, and that the earliest chapter is still missing. In the next chapter, we follow the leading framework that answers those puzzles. Inflation becomes the bridge between what we can model and what we still cannot, and it gives the universe a prelude with testable consequences. And the question changes shape again, from a beginning in time to a mechanism that may have set the stage for time as we know it, leaving us with one final quiet thought. When the stage itself is dynamical, what does it mean to ask what came first? The Hot Big Bang fits the evidence, yet it begins with suspicious order, an order that looks almost staged when we run the film backward. The cosmic microwave background, the CMB, is uniform across vast angles, and space is nearly flat today, which sounds mundane until you ask how improbable it was. Those facts look ordinary now, especially on a star-filled night, but they were unlikely in the simplest rewind. On screen, the universe becomes a pale, glowing fog, and then a tighter, brighter haze as we rewind toward earlier times. Temperature rises, particle energies climb, and the plasma becomes so dense that light cannot travel freely, because photons are trapped in constant scattering. Yet the closer we push toward the beginning, the more the initial state seems oddly arranged, smooth, balanced, and delicately poised, as if someone tuned the starting conditions. Here we meet the boundary of evidence and the boundary of theory. The data describe a hot plasma after reheating, and they map its ripples with exquisite accuracy. But they also hint at an earlier setup hidden behind that curtain. Inflation enters as that setup, an early episode of accelerated expansion that reshapes what beginning can mean, and it does so with a surprisingly economical mechanism. Inflation is not expansion in the everyday sense of objects moving outward through space. It is the scale factor growing with positive acceleration, often close to exponential for a short time, so that distances between co-moving points increase astonishingly fast. In that brief window, a tiny region becomes enormous, and the geometry we later measure is effectively stamped into place, like a seal pressed into wax. Visually, imagine a faint grid drawn on space itself, with galaxies as dots pinned to the grid. During inflation, the grid stretches so rapidly that the dots separate, not by flying outward, but because the underlying ruler is changing. The effect is so extreme that the word growth spurt feels literal. Space swells as if driven by a hidden pressure, and the camera struggles to keep the grid in frame. This is why inflation can sound like it breaks relativity, yet it does not. Relativity forbids objects from outrunning light through local space, not the growth of space itself, which is encoded in the evolving metric. In general relativity, the metric can change so that separation grows faster than light, without any local superluminal motion, and no local law is violated. The key is locality, and it matters more than the headline phrase, faster than light. Every observer still measures nearby light moving at sea, and local physics remains causal, with signals confined to light cones. The faster than light description refers to global separation between distant points, which is not a message, not a rocket, and not an exploit, just geometry evolving. A useful visual is a light cone drawn on a stretching grid. The cone's angle stays the same locally while the grid lines pull apart, so distant points drift beyond what any signal can reach. Inflation is not a loophole in causality. It is a reshaping of which regions were ever in causal contact, and that reshaping is the whole point. Inflation was proposed to solve specific puzzles that Chapter 3 sharpened, and it arrived with a striking historical timing. In the late 1970s and early 1980s, particle physics was grappling with symmetry breaking and phase transitions, while cosmology was absorbing new precision about the early universe. In that moment, inflation appeared as a synthesis, linking high-energy fields to cosmic-scale geometry, with names like Guth, Linde and Albrecht and Steinhardt shaping the early debate. The horizon problem asks why distant CMB regions share nearly the same temperature, despite appearing causally disconnected in a simple, hot big bang. The flatness problem asks why curvature is so close to zero, despite being unstable under ordinary decelerating expansion. And the relic problem asks why predicted heavy leftovers from early physics are not piled up in the universe today, as if the universe cleaned up after itself. Start with the horizon problem, because it is the one you can almost see. The CMB is a photograph of the universe when it first became transparent, roughly 380,000 years after the hot beginning, when electrons and nuclei combined into neutral atoms. Before that moment, photons scattered constantly off free electrons, and the universe was an opaque plasma, like a glowing fog that never lets you see far. At recombination, the fog thinned, and light began to stream freely, carrying a snapshot of temperature across the sky. We measure that snapshot as a blackbody spectrum at about 2.7 Kelvin, with tiny anisotropies at the level of 1 part in 100,000. Those anisotropies form a delicate mottled pattern, like faint freckles on an otherwise uniform sphere, and their statistics are as informative as their beauty. In a non-inflating hot Big Bang, the particle horizon at recombination is too small. Opposite sides of the CMB sky were never in thermal contact, yet their temperatures match to 1 part in 100,000. The puzzle is not that the universe is smooth, but that it is smooth across regions that, by the simplest accounting, never had time to agree even once. The horizon here is not a physical wall, it is a limit set by light travel time in an expanding space-time. If two regions cannot exchange signals, they cannot share heat, pressure or information, so their temperatures should be uncorrelated. Yet the CMB looks like a single, coherent thermal bath, with only tiny deviations, as if it once sat in the same cosmic room. Inflation changes the causal story by changing the prehistory of the patch we observe. Before inflation, the region that becomes our observable universe can be small enough to equilibrate through ordinary interactions. During inflation, that once connected patch is stretched far beyond the later horizon size, so it appears as many disconnected regions that nonetheless share a common past, and that shared past is the hidden glue. Uniformity becomes a memory of an earlier closeness, not a miracle of late-time coordination. Inflation does not let information travel faster than light, and it does not ask distant regions to communicate after they are separated. It makes the region that needs coordinating originate from a smaller, causally connected domain, then magnifies it until it fills our sky. A vivid way to picture this is to imagine a tiny, warm drop of fluid that has time to settle into a uniform temperature. Inflation then stretches that drop into something vast, so that the same initial warmth is smeared across a cosmic volume. The later universe inherits that uniformity, like a signature left by an earlier, tighter world, and the CMB becomes the ink. Now the flatness problem, which is subtler but just as sharp. In the Friedmann equations, curvature behaves like a term that becomes more important in a decelerating universe, because matter and radiation dilute, while curvature dilutes more slowly. If the universe is even slightly curved early on, that curvature tends to grow in relative importance over time, making today's near flatness feel precarious. To be this close to flat today, the early universe would need extreme fine-tuning of curvature. The density parameter O must have been extraordinarily close to 1 to many decimal places at early times. Without a mechanism, it feels like balancing a pencil on its tip and finding it still upright billions of years later, despite every vibration. Inflation drives the geometry toward flatness dynamically, and it does so with a simple geometric intuition. Rapid expansion makes any initial curvature radius enormous compared to the observable patch, so the part we can measure looks flatter and flatter. Like stretching a curved surface until it looks locally flat, inflation makes near-critical density an attractor outcome, not a lucky accident. The analogy is not perfect, but it is helpful for the eye. A sphere is curved, yet a small patch can look like a plane, and the larger the sphere's radius, the flatter the patch appears. Inflation effectively increases the radius of curvature so dramatically that our observable region becomes a tiny, nearly Euclidean piece of a much larger geometry, even if the whole remains curved. Then there is the relic problem, often illustrated with magnetic monopoles. Many high-energy theories predict heavy defects formed in early-phase transitions, the way cracks can form when water freezes into ice. In grand unified scenarios, monopoles can be produced copiously, and because they are massive and stable, they would linger, turning the early universe into a museum of unwanted artifacts. Without dilution, their number density would be high enough to dominate the universe, altering expansion and leaving unmistakable signatures. Yet we do not see them, despite decades of searches in cosmic rays, ancient minerals, and specialized detectors. The absence is not merely disappointing, it is a boundary condition that any early universe story must respect, whether it likes it or not. Inflation dilutes relics by expanding volume dramatically while keeping relic number roughly fixed. A huge increase in scale factor turns common into rare without needing exotic destruction mechanisms. The absence of monopoles becomes consistent with theories that would otherwise overproduce them, and the same logic applies to other heavy leftovers that would have cluttered the cosmos. In visuals, the relics are like a handful of heavy beads scattered on a rubber sheet. Stretch the sheet by an enormous factor, and the beads become separated by such vast distances that encountering one becomes unlikely. Inflation does not forbid relics, it makes them cosmically scarce, hiding them in the sheer size of space. So inflation looks like a clean fix, yet it must also explain the universe's structure. The CMB is not perfectly uniform, and it contains a specific pattern of tiny fluctuations, arranged in a way that is statistical but not random in the naive sense. Those fluctuations seed galaxies, clusters, and the large-scale web, the filaments and voids that surveys now map across billions of light-years, like a cosmic nervous system. The remarkable thing is that structure is both delicate and inevitable. Without fluctuations, gravity would have nothing to amplify, and the universe would remain a smooth gas forever. With fluctuations that are too large, the universe would collapse into black holes and dense clumps too early, leaving little room for the slow evolution of stars and chemistry, and the night sky would be unrecognizable. Inflation provides a mechanism for those seeds through quantum fluctuations. Quantum fields cannot be perfectly still, even in their lowest energy state, because uncertainty is built into the fabric of measurement, and vacuum is never truly empty. During inflation, vacuum fluctuations are stretched from microscopic scales to astronomical wavelengths, and their imprint becomes the blueprint for later structure, written in the language of probability. The stretching matters because it freezes fluctuations into classical-looking perturbations, and this is one of inflation's most subtle claims. Modes begin well inside the horizon, where they behave like ordinary quantum oscillations with well-defined frequencies. As inflation expands space, wavelengths exceed the horizon scale, and the perturbations become effectively locked in, no longer averaging away. The horizon here is the Hubble radius, roughly the distance beyond which expansion prevents causal contact at that time. When a mode crosses outside, its oscillations stop evolving in the same way, and its amplitude becomes nearly constant. In plain terms, inflation takes jittery quantum noise and turns it into a stable pattern, like ripples caught in ice, waiting to thaw. Later, after inflation ends, the horizon grows again in the standard hot Big Bang. Those frozen modes re-enter the horizon and become density variations that matter can respond to. Gravity amplifies the overdensities, while pressure and radiation shape the acoustic signatures, leaving a ringing pattern in the CMB, and those rings become a ruler for cosmic history. Those acoustic signatures are not metaphorical. They are real sound waves in the primordial plasma. Photons and baryons were tightly coupled, so compressions heated the plasma and rarefactions cooled it, producing oscillations. When the universe became transparent, those oscillations were frozen into the light, and we now read them as peaks in the CMB power spectrum, like harmonics in a chord. This story makes a sharp prediction about statistics, and the CMB has become the courtroom where it is cross-examined. Many inflation models produce perturbations that are nearly Gaussian and adiabatic, meaning they resemble a random field with a bell curve distribution and shared fractional density changes across components. They also produce a nearly scale-invariant power spectrum, meaning similar fluctuation strength per logarithmic interval of scale, with only a gentle tilt. Scale invariance is a technical phrase with a simple implication. If you zoom in or out by a factor, the pattern's strength does not change dramatically, so the universe looks statistically similar across a wide range of sizes. Inflation predicts a slight deviation from perfect scale invariance, and that deviation becomes a clue to the microphysics, like a fingerprint smudged but still readable. The CMB measures that spectrum with precision, turning the sky into a data set of extraordinary depth. The scalar spectral index NS is close to, but not exactly 1, and that not exactly is where physics hides. That slight tilt is a clue that inflation was not perfectly exponential, and it points towards slow evolution during the inflationary phase, rather than a perfectly constant vacuum energy. On screen, the power spectrum appears as a smooth curve with peaks, and then we zoom into the tilt, a gentle slope that would be easy to miss without precision. It is a reminder that cosmology is often about small differences that accumulate into large conclusions. A few percent deviation in NS can rule out whole families of potentials, and it can elevate others from speculation to serious contenders. To understand what we can ask, we start with what we can calculate. Inflation is often modelled with a new ingredient called the inflaton, a hypothetical field whose energy density dominates briefly and drives accelerated expansion. The inflaton is not a single agreed upon particle, and that uncertainty is part of the story rather than an embarrassment, because multiple microphysical candidates can mimic the same cosmic behaviour. In the simplest picture, the inflaton sits on a potential energy landscape, like a ball on a gently sloped plateau. When potential energy dominates over kinetic energy, pressure becomes negative, and that sign matters in general relativity. In Einstein's equations, not only energy density but also pressure gravitates, and sufficiently negative pressure can cause accelerated expansion, meaning gravity effectively becomes repulsive on large scales. This is the slow roll idea, and it is both elegant and constrained. The inflaton rolls gradually down its potential, so the energy density changes slowly and inflation lasts long enough to stretch a tiny patch into something enormous. Slow roll parameters quantify how flat the potential must be to sustain near exponential growth, and they connect directly to observables like S and R, tying abstract calculus to the sky. The mathematics is compact, but the physical picture is vivid. A nearly constant energy density acts like an almost constant vacuum energy, and that vacuum-like state drives space to expand at an accelerating rate. If the potential is too steep, the field rolls too fast, inflation ends too quickly, and the horizon and flatness puzzles return, as if the universe never had time to smooth its wrinkles. Inflation must also end, or the universe would remain cold and empty, a vast expanding vacuum with no stars and no chemistry. Ending inflation requires the inflaton to leave the slow roll regime, either because the potential steepens or because the field reaches a critical point. The field begins to oscillate or decay, converting its energy into particles, and the cosmic stage changes its lighting. That conversion is reheating, and it is where the familiar hot Big Bang begins. Reheating repopulates the universe with radiation and matter, setting the initial temperature for the standard thermal history, including nucleosynthesis and later recombination. In this framing, the Big Bang is not the start of everything, but the aftermath of inflation, the moment the universe becomes a hot, interacting plasma again. Visually, reheating is a dramatic transition, like a dark stage suddenly flooded with light. The smooth, cold, inflating space becomes filled with a hot bath of particles, collisions, and radiation, and the universe becomes a thermal system again. The phrase hot Big Bang regains its literal meaning at this moment, because temperature becomes a meaningful shared property, not just a metaphor. Reheating is both essential and uncertain, and the uncertainty is not a minor detail. It depends on how the inflaton couples to known particles or to hidden sectors, and those couplings determine how efficiently energy is transferred. Different reheating histories can change the number of E-folds required and can shift predictions for observables, because the mapping between scales and times depends on what happened after inflation, in the murky interval before the universe settled. An E-fold is a simple unit with an enormous implication. It is a factor of E, about 2.718, in the scale factor's growth. Dozens of E-folds can turn a subatomic region into something macroscopic, and around 60 E-folds can be enough to encompass our observable universe. The exact number depends on reheating, which is why reheating uncertainty echoes back into inflation's predictions, like an unknown epilogue changing how you interpret the opening chapter. Inflation's success therefore comes with model building choices, and those choices can be both creative and dangerous. We can write many potentials, many couplings, and many initial conditions, and we can often tune them to match broad features. The challenge is to keep inflation predictive rather than endlessly adjustable, so that it remains a scientific explanation rather than a flexible story, and that challenge is part of its modern tension. Observations help by narrowing the space of viable models, and the CMB has become a precision instrument for early universe physics. The temperature anisotropies and polarization constrain the amplitude and shape of the scalar spectrum, and they also constrain non-Gaussianity. Many simple slow-roll models predict non-Gaussianity to be small, and so far the data agree, tightening the noose around more exotic scenarios that would leave sharper statistical fingerprints. Polarization deserves a moment, because it is a second layer of information painted onto the same sky. Thomson scattering in the early universe produces polarization when radiation has a quadrupole anisotropy, and that polarization can be decomposed into E modes and B modes. E modes are already measured with high precision, and they reinforce the acoustic story of the photon baryon plasma, matching the peaks like a second instrument in the same orchestra. Another key target is tensor modes, primordial gravitational waves, which are ripples in spacetime itself. Inflation generically produces tensor fluctuations, because quantum mechanics also perturbs the metric, not just matter fields. Their amplitude is often summarized by the tensor-to-scalar ratio R, which depends on the energy scale of inflation and the field's dynamics, turning a polarization map into an energy probe. Tensor modes would leave a distinctive imprint in CMB polarization, and the signature is geometrically specific. They can generate a primordial B-mode pattern at degree-angular scales, a swirling pattern that cannot be produced by scalar density perturbations alone. Detecting that pattern would be a direct window into inflationary dynamics, and it would tie the early universe to quantum gravity in a tangible way, because it would be quantum fluctuations of spacetime made visible. So far, no definitive primordial B-mode detection has survived scrutiny, and the history here is instructive. Experiments have measured B-modes dominated by gravitational lensing and by astrophysical foregrounds like dust emission, which can mimic the signal. Upper limits on R now rule out many high-energy, large-field inflation models, especially those with simple monomale potentials, and they force theorists to be more careful about what natural should mean. The absence is not a refutation of inflation as a broad idea, and it should not be narrated as a failure. It is a constraint that forces inflation into narrower corners of parameter space, favoring lower tensor amplitudes or more complex dynamics. It also raises the stakes for future measurements, because each improvement can eliminate entire classes of potentials, and each null result is still a result. In visuals, we see telescopes at the South Pole and in the Atacama Desert, scanning the sky in thin arcs. We overlay maps of polarized dust, then subtract models, then watch the remaining signals shrink into error bars. The suspense is scientific. Nature is not obliged to give us a large R, even if our theories once hoped for it, and the sky does not negotiate. There are other tensions and subtleties, and they live in the details of the spectrum. Some inflation models predict features in the power spectrum, bumps, oscillations, or sharp steps, that are not seen. Others require initial conditions that seem special, which can feel like the original fine-tuning problem returning in new clothing, and the unease is hard to ignore. Even the horizon solution has a hidden assumption, and it is worth stating plainly. Inflation must start in a region already smooth enough for accelerated expansion to begin, because large gradients or anisotropies can prevent the vacuum-like state from dominating. If the pre-inflationary state is too chaotic, inflation may not start or may not last, and the elegant fix becomes conditional. This is the deeper question behind the solution, and it is where the tone becomes more mysterious. Inflation explains why our patch is smooth and flat if inflation occurred, and it explains it with impressive economy. It does not automatically explain why inflation started, why it had the right duration, or why it ended into the state we infer, and those missing steps feel like a shadow behind the spotlight. That brings us back to the central question, now sharpened rather than softened. If the Big Bang marks the beginning of our observable universe, what can science say about the cause or conditions that led to it? Inflation shifts the beginning earlier, but it does not eliminate the need for an origin story, and it makes the origin story more technical. The origin question becomes a question about initial conditions for inflation, and those conditions are not trivial. What set the inflaton high on its potential, or placed it in a slow roll region, rather than letting it fall quickly into a non-inflating phase? What selected the vacuum state of fluctuations, and why that state looks like the simplest choice, often approximated as the bunch, Davy's vacuum, as if the universe began in the cleanest quantum posture? The vacuum choice matters because it sets the initial quantum state for modes that later become cosmic structure. If the state were excited or modified, the power spectrum could carry signatures, such as altered correlations or non-standard features. The fact that the observed spectrum is so clean is both a triumph and a constraint, as if the universe is telling us it began in a remarkably simple quantum condition, even when complexity was available. Some approaches treat inflation as generic, arising from many starting states because expansion can iron out wrinkles once it begins. Other approaches find it fragile, requiring a special patch and special homogeneity to ignite the process. The debate is technical, but the narrative meaning is simple. Does inflation reduce fine-tuning, or relocate it, moving the mystery rather than dissolving it? At this point, it helps to remember what the evidence actually is. We do not observe inflation directly, like a fossil in rock, but we infer it from the pattern of perturbations and from the large-scale geometry. Inflation is a proposed prelude that makes the observed song easier to sing, yet the prelude itself remains partly hidden behind the curtain of reheating, where direct traces may have been erased. Then inflation opens an even stranger door called eternal inflation, and the door creaks on quantum hinges. In some potentials, quantum fluctuations of the inflaton can compete with its classical role, adding a random walk on top of a steady drift. In some regions, the field fluctuates upward enough that inflation continues locally, even while other regions roll down and end, and the process becomes self-sustaining. If inflation continues in some regions while ending in others, the universe becomes a patchwork. Regions where inflation ends reheat and form bubble universes, each with its own hot beginning and its own subsequent expansion. Regions where it continues keep expanding, creating more volume and more chances for new bubbles, so the inflating background never fully disappears, and the word end becomes local. This is not a multiverse added for drama, and it is not merely a philosophical flourish. It is a dynamical consequence in many inflationary models once quantum fluctuations are taken seriously, because fluctuations are not optional in quantum field theory. The overall spacetime keeps inflating, while pocket universes like ours appear as local endings, like islands forming in a rising sea. In that picture, our Big Bang is not the absolute beginning, and that shift is emotionally as well as scientifically significant. It is a transition event inside a larger inflating background, like a local thaw in a much larger frozen landscape. The question, what caused the Big Bang, becomes what caused our bubble to nucleate or our region to exit inflation, and the answer may be probabilistic rather than mechanical. Eternal inflation also changes what prediction means, and this is where the mystery deepens rather than resolves. If many bubbles exist with different low-energy physics, then observed parameters might be environmental, selected because they allow complex structures to form. The theory risks becoming statistical, with selection effects and anthropic reasoning entering the conversation, and that shift can feel like a change in the rules of explanation. That shift forces an uncomfortable question. Are we explaining the universe? Or are we explaining why we see this particular corner of it? In a statistical multiverse, some outcomes happen somewhere simply because there is so much somewhere, and probability becomes entangled with measure problems. Even the phrase typical observer becomes slippery because infinity does not behave like a large number, and counting becomes a conceptual trap. This is where inflation's power becomes a deeper mystery. It can explain why our observable universe looks simple, yet it may imply a reality that is wildly diverse beyond our horizon. It can make the beginning less like a point and more like a branching process, with countless endings of inflation marking countless hot beginnings, each one locally dramatic and globally routine. But the multiverse idea faces hard questions of testability, and the documentary must linger on that boundary. If other bubbles are causally disconnected, direct observation may be impossible, because no signal can cross the inflating regions between them. Some proposals search for indirect signatures, like bubble collision imprints in the CMB, but evidence remains uncertain and the searches are methodologically delicate, because false patterns can arise from noise and foregrounds. Even without a multiverse, inflation still raises energy source questions that do not go away. What is the inflaton field physically, and why does its potential have the required shape? Flat enough to slow roll yet structured enough to end? Is it related to known fields, perhaps connected to particle physics beyond the standard model? Or is it entirely new physics, hiding in a sector we have not yet touched? The potential is not just a curve on paper, it encodes a microphysical theory. Different potentials correspond to different symmetries, different interactions, and different radiative corrections, and those corrections can spoil flatness unless protected. So inflation quietly asks particle physics for a field that behaves in a very special way under quantum corrections, an ask that is plausible, but not yet answered, and not guaranteed. Inflation also touches quantum gravity, because the earliest moments may sit near energies where space-time itself becomes quantum. When energy densities approach extreme scales, our classical description of geometry may become an approximation, and the meaning of before can blur. Some arguments suggest inflation cannot be extended arbitrarily far into the past, even classically, implying a boundary to inflationary time, like a horizon in the narrative itself. That boundary is not necessarily a singularity in the old sense, but it is a limit to the story inflation can tell by itself. If inflation had a beginning, then the origin question returns once more, now pushed to an even more abstract edge. We are left asking what sets the initial state of the inflating space-time, and whether initial is even the right word when time may be emergent. So inflation is a bridge, not a final foundation, and bridges are defined by what they connect. It links the observed CMB and structure to a plausible early mechanism, and it explains why the universe looks so uniform and so nearly flat. Yet it also pushes the origin question into a regime where our concepts of time, vacuum, and causation become less secure, and where language starts to strain. We can summarize what inflation achieves and what it costs without losing the tension. It explains horizon uniformity by stretching a once-connected patch, and it does so without violating relativity's local speed limit. It drives curvature toward flatness and dilutes relics, while generating the nearly scale-invariant seeds of structure that the CMB reveals, and it ties quantum uncertainty to the architecture of galaxies. And it costs us new unknowns, which are not small unknowns. It introduces an inflaton and a potential we have not identified in particle physics, and it demands a beginning for inflation and a mechanism for reheating. It may imply eternal inflation and a multiverse, turning the question of the beginning into a question about global structure, where our patch is one outcome among many. This chapter's suspense is that the solution multiplies the questions, and that multiplication is part of science's honest rhythm. Inflation makes the early universe more intelligible, yet it makes the ultimate origin less singular and less point-like. The beginning becomes a process, and the process demands its own explanation, which may lie in deeper principles we have not yet earned. Here we meet the boundary of evidence and the boundary of theory again. The CMB encodes the perturbations with exquisite precision, and those measurements increasingly constrain inflation's simplest forms, tightening around n's, non-Gaussianity, and R. Yet the trigger, the field, and the global picture remain uncertain, and the uncertainty is not a void but a frontier, where better data and better ideas have room to meet. The central question therefore evolves rather than resolves. If the Big Bang is the hot aftermath of inflation, then the cause of the Big Bang may be the end of inflation, a graceful exit into a thermal universe. But the cause of inflation, and the meaning of cause near the boundary of time remain open, and the openness is the point. Next, we follow that opening into competing ideas about beginnings, and we do it with the same discipline that inflation demanded. Some will try to replace inflation, others will embed it in deeper frameworks, and some will reinterpret what beginning even means. All of them will confront the same haunting edge: how far science can push toward a first page when the book may not start with time at all. We keep chasing the same question, and it keeps changing shape as our theories sharpen and mature. If the Big Bang marks the beginning of our observable universe, what, if anything, can science say about the cause or conditions that led to it? Chapter 4 made inflation a powerful prelude, yet it also pushed the mystery backward into deeper territory. Inflation can end in reheating, and reheating can look like a hot beginning when we run the film in reverse. But inflation still needs a stage, and the stage itself may be quantum, restless, probabilistic, and not fully describable as classical spacetime. Now the story turns on one word that sounds simple and is not: nothing. In everyday speech, nothing means absence, emptiness, and zero, the cleanest possible blank. In modern physics, nothing is rarely an allowed state, because the theories that describe nature already contain structure. Even our most careful equations begin with ingredients, fields, symmetries, and rules for how quantities can be measured. When we say nothing in a physical context, we usually mean no particles, or no classical matter, not no underlying degrees of freedom. That difference seems technical at first, yet it determines what questions are even well posed. To understand what we can ask, we start with what we can calculate. Quantum field theory does not treat space as an empty container waiting to be filled. It treats space as the arena where fields exist everywhere, even when no particles are present. A field, in this sense, is not a poetic haze spread across the cosmos, but a precise mathematical object. It assigns a value, or in quantum terms an operator, to every point in spacetime. The electromagnetic field is the familiar example, yet the standard model is built from many fields, each with its own quantum excitations. The electron field, the quark fields, the gluon field, and the Higgs field all permeate space in this description. What we call a particle is a particular excitation pattern of one of these fields. The universe, even in apparent darkness, is threaded with these ever-present ingredients. In this framework, particles are not fundamental marbles drifting through a void. They are localized quanta, like discrete ripples, of underlying fields that never truly switch off. The language of empty space becomes a shorthand for a particular state of those fields. A vacuum in quantum field theory is not no stuff. It is the lowest energy state of fields, defined relative to a chosen notion of energy. Even that definition depends on the geometry of spacetime and on what counts as time translation. That last phrase matters, because energy is tied to time in physics through a deep symmetry principle. In a static spacetime with a clear time symmetry, we can define a stable ground state with confidence. In an expanding universe or near strong curvature, the very notion of lowest energy can become subtle and observer-dependent. This is why different observers can disagree about what counts as a particle, even when they agree on the underlying field. In curved spacetime, the split between vacuum and excitation can shift with the choice of time coordinate. The vacuum is not merely a place, it is a relationship between fields and geometry. Fields cannot be perfectly still because uncertainty is built into their observables. Even in the ground state, field amplitudes and conjugate momenta fluctuate, constrained by commutation relations. Those fluctuations are not optional noise, they are the structure of the theory. A useful mental image is a violin string that cannot lie perfectly flat, even when untouched. Quantum mechanics forbids exact stillness, because fixing one quantity precisely forces uncertainty in another. The vacuum is therefore not a blank frame, but a state with irreducible jitter. In equations, that jitter shows up as a non-zero zero-point contribution, the baseline energy of each mode of a field. Each mode behaves like a quantum harmonic oscillator, and its lowest energy is not zero. The vacuum in this sense is a sea of minimum energies that never quite vanish. Popular accounts talk about virtual particles popping in and out of existence, as if the vacuum were a bubbling cauldron. That phrase is a heuristic, not a literal movie of tiny objects appearing. Virtual particles are internal bookkeeping and perturbation theory, tied to terms in an expansion. They show up as internal lines in Feynman diagrams, which are tools for organizing calculations rather than photographs of microscopic events. In many contexts, the same physics can be computed without invoking the pop-in, pop-out story at all. The vacuum's activity is real, but the cartoon can mislead. The safer statement is about correlations and fluctuations that can be measured in principle. The vacuum has non-zero two-point functions, meaning field values at separated points are statistically linked. It responds to boundaries and curvature, and it can store information in its pattern of correlations. These correlations are not just mathematical decoration, because they determine how detectors would click. They also underwrite why quantum noise has a characteristic structure, rather than being arbitrary randomness. Even nothing, when treated carefully, has a texture. What looks like emptiness can still push, pull, and polarize. The vacuum can be distorted by the presence of matter, and it can influence matter in return. In quantum theory, the baseline state is not inert. It is a medium in the precise sense that it can be modified and can have measurable consequences. The Casimir effect is the cleanest reminder that empty space has measurable structure. Two uncharged conducting plates in vacuum attract because boundary conditions change the allowed field modes. The force is small, but it is real and repeatable. Visually, imagine two mirror-like plates facing each other in a dark chamber, separated by a hair's breadth. Between them, only certain electromagnetic standing waves can fit, like notes allowed in a narrow organ pipe. Outside the plates, many more modes are permitted, and the imbalance produces a pressure difference. A helpful way to picture it is as a difference in the vacuum's hum, quieter between the plates and louder outside. The plates do not create the vacuum fluctuations, but they filter them. The result is a tiny net force that becomes noticeable when the gap is microscopic. The effect is not a mysterious new force added by hand. It is a shift in the vacuum's zero-point energy due to constraints on the field. In the lab, the attraction can be measured with delicate torsion balances and microfabricated devices, where nanometer distances matter. Historically, the Casimir prediction in 1948 arrived in the same era as modern quantum electrodynamics was being forged. It was a reminder that the vacuum state is not just a convenient baseline for calculations. It is a physical state whose properties can be altered by geometry. Vacuum fluctuations also show up indirectly in atomic physics. The Lamb shift reflects how the electromagnetic vacuum modifies energy levels in hydrogen. The details require renormalization, but the message is simple. The vacuum is an active participant in the quantum sense. One can imagine the electron in hydrogen not orbiting like a planet, but existing as a smeared probability cloud. That cloud interacts with the fluctuating electromagnetic field, which slightly shifts the allowed energies. The shift is tiny, yet it is consistent and measurable. Historically, this was one of the moments when quantum electrodynamics proved its power. Tiny spectral shifts, once puzzling, became precise tests of a theory built on fields and fluctuations. The vacuum was no longer philosophical, it was a measurable ingredient. Renormalization itself is a clue to how nothing resists simplicity. The raw calculations often produce infinities, which are not accepted as literal physical predictions. Instead, the theory is reorganized so that measurable quantities remain finite, and the vacuum's contributions are handled with care. Renormalization can feel like sweeping dust under a rug, yet it is better understood as a disciplined accounting method. We define parameters like charge and mass by how they are measured, not by how they appear in intermediate steps. The vacuum's influence is real, but it must be expressed in observable terms. This matters for cosmology because the early universe is not just hot matter in space. It is matter, radiation, and fields interacting with a dynamical geometry that can stretch and curve. If we ask what caused the Big Bang, we're asking what the vacuum and geometry were doing at the boundary. At that boundary, the usual separation between stuff and stage begins to dissolve. In general relativity, space-time is not a fixed background, because energy and pressure shape curvature. In quantum theory, the vacuum is not empty, because fields retain fluctuations even in their ground state. Here we meet the boundary of evidence and the boundary of theory. We can test quantum fields on fixed backgrounds with extraordinary precision, from particle accelerators to atomic clocks. We cannot yet test quantum gravity in the regime where the background itself fluctuates. The Planck scale marks the region where our current concepts strain. It is not merely a number, but a warning sign that quantum effects of spacetime itself may become unavoidable. When lengths approach 10⁻⁵ meters, the smooth geometry used in relativity may no longer be a reliable approximation. At those scales, even the idea of a sharply defined distance becomes questionable, because measurement would require energies that strongly curve spacetime. The act of probing can disturb what is being probed, not just by quantum backaction, but by gravity itself. The boundary is physical, not just philosophical. Still, the vacuum is not a side character in the universe we see today. The accelerated expansion of the present universe points to dark energy, inferred from how cosmic distances evolve. In the simplest model, dark energy behaves like a cosmological constant, a uniform energy density of the vacuum. A cosmological constant is not a particle cloud drifting through space. It is a term in Einstein's equations that acts like energy with negative pressure. Negative pressure changes how gravity works on large scales, producing accelerated expansion. In everyday terms, gravity usually pulls things together, and expansion should slow down. A cosmological constant behaves differently because its energy density remains roughly constant as space expands. As the universe grows, the total vacuum energy in a larger volume increases, and the effect on expansion can dominate. You can visualize this as a grid drawn on an elastic sheet, with galaxies riding the intersections. As the sheet stretches, matter thins out, but the vacuum-like component does not dilute in the same way. Over billions of years, that difference becomes decisive. Observations support that acceleration through multiple lines of evidence. Type Ia supernovae trace the late-time expansion history by serving as standardizable candles. The CMB and baryon acoustic oscillations cross-check the geometry and matter content with independent cosmic rulers. The evidence is not a single dramatic measurement, but a convergence. Different methods with different systematics point to the same broad conclusion. The expansion is speeding up. The vacuum, or something that mimics it, is shaping the fate of the cosmos. So vacuum energy seems to matter, but it arrives with a brutal puzzle. Naive quantum estimates of zero-point energy are enormous, because every field mode contributes. The observed value is tiny by comparison, smaller by many orders of magnitude. This is the cosmological constant problem, and it is not a minor mismatch. If we cut off vacuum modes at high energies, the predicted energy density is catastrophically large. The universe would curl up or blow apart far too fast for galaxies to form. The severity is hard to overstate because the discrepancy is not a factor of 2 or a factor of 1,000,000. Depending on assumptions, it can be tens of orders of magnitude, a gap that makes theorists uneasy. It suggests that our understanding of vacuum energy and gravity is incomplete. One reason the puzzle bites so hard is that quantum field theory is otherwise spectacularly successful. The same framework that predicts the Lamb shift and the magnetic moment of the electron also predicts a vacuum energy that seems wildly wrong. The tension feels like a message written in the theory's own handwriting. We do not know why the vacuum gravitates so weakly, or why cancellations would be so precise. Some ideas invoke symmetry, like supersymmetry, which can cancel contributions between bosons and fermions. But it is broken at accessible energies, so the cancellation cannot be exact. Some invoke selection effects, where many possible vacuum energies exist, and observers arise only in the rare hospitable cases. That shifts explanation into statistics rather than dynamics, and it raises questions about what counts as a prediction. The puzzle remains a pressure point in fundamental physics. The key point for this chapter is narrower and more unsettling. The vacuum is not nothing, and its energy is not a free detail we can ignore. If vacuum energy shapes cosmic expansion now, it likely mattered near any beginning. So what does it mean to say the universe came from nothing? In physics, nothing might mean no classical spacetime, no matter, and no time parameter. But quantum theories are written with mathematical structures that already assume rules. A blank page, in the absolute sense, would contain no equations to write. Yet physics is, by design, a description of regularities, and regularities require a framework. That tension sits at the heart of creation from nothing claims. When a paper says creation from nothing, it often means something technical, not a metaphysical absolute. It can mean tunneling from a state with no classical geometry into a state with a small closed universe. It can mean a boundary condition on the wave function of the universe. These are attempts to replace a classical singularity with a quantum description. They do not claim a literal empty box existed first, waiting to be filled. They claim the classical notion of space-time breaks down, and a quantum state must replace it. The historical backdrop matters here, because singularities were once treated as mere mathematical oddities. The Penrose, Hawking singularity theorems, developed in the late 1960s and early 1970s, changed that attitude. Under broad conditions, classical relativity predicts geodesic incompleteness, an edge where the theory stops. Geodesic incompleteness sounds technical, so translate it into an image. Imagine tracing the path of a particle backward in time, expecting the line to continue smoothly. The theorems say that, under reasonable assumptions, the line simply ends, not because we ran out of patience, but because the geometry cannot be extended. Quantum cosmology emerged as a response to that edge. If classical spacetime fails, perhaps quantum principles provide a continuation, not by extending time backward, but by replacing the classical description entirely. The goal is modest and radical at once, to make the beginning a domain of calculation. Quantum cosmology begins with a hard choice. Do we quantize gravity in a mini-superspace model, reducing the universe to a few degrees of freedom? Or do we attempt a full theory where geometry has infinitely many modes? The first is tractable, the second is the real target. Mini-superspace is a controlled simplification, like studying ocean tides by tracking only the largest waves. We keep the scale factor, perhaps a homogeneous inflaton field, and ignore most inhomogeneities. It is not the final word, yet it can reveal how quantum rules reshape cosmological questions. In mini-superspace, the scale factor becomes a variable, like a coordinate in a reduced configuration space. One writes an equation resembling a Schrödinger equation, often called the Wheeler-DeWitt equation. It is not evolution in time in the usual sense. The Wheeler-DeWitt equation looks timeless because the Hamiltonian constraint equals 0. The wave function depends on geometry and matter fields, not on an external clock. This is not philosophy added later, it is a feature of the formalism. In ordinary quantum mechanics, the Schrödinger equation tells a state how to change with time. Here, the equation instead imposes a constraint on allowed states, like a rule that selects consistent patterns. The universe is not placed in time from the outside because there is no outside. That idea can feel slippery because we experience time as relentless and obvious. Yet in the formalism, what we call time can be a parameter extracted from correlations, not a fundamental input. The equations invite a strange question. If the universe is timeless at the deepest level, why does time feel so real? From this framework come proposals that sound like origin stories. One family is tunneling proposals, often associated with Vilenkin and others. The universe nucleates as a quantum event, like barrier penetration in ordinary quantum mechanics. The picture is that a small closed universe can appear with some probability amplitude. Its size is set by the energy scale, often tied to an effective vacuum energy. After nucleation, classical expansion can take over, possibly with inflation. For visuals, imagine a contour map of a landscape, where valleys represent classically allowed regions. A quantum state can leak through a ridge into a neighbouring valley, even when classical motion forbids it. In cosmology, the ridge is not a wall in space, but a barrier in configuration space. The word tunneling is tempting because it suggests a before and after, but in the formalism, before is not a time coordinate outside the universe. It is a region of configuration space where classical trajectories are forbidden. So the claim is not that time existed in nothingness, and then started. The claim is that the wave function has support on geometries that are not classically allowed. A classical universe can emerge from a quantum regime without a classical past. That emergence is subtle, because classical behaviour must be recovered from quantum rules. In practice, one looks for semi-classical approximations, where phases vary rapidly and trajectories become meaningful. The universe looks classical when interference between alternative histories becomes negligible, and a single branch dominates. This is where decoherence quietly enters the origin story, even if it is not always named. Interactions among degrees of freedom spread phase information into inaccessible correlations, making alternatives effectively non-interfering. The result is not a mystical collapse, but a practical separation into branches that behave classically. Another approach is the Hartle, Hawking no-boundary proposal. It treats the origin as a smooth rounding, not a sharp edge. The universe's wave function is computed by summing over compact Euclidean geometries with no boundary. In that picture, the beginning is like the south pole of the Earth. It is a point where latitude is defined, but there is no edge to cross. Time emerges gradually as the geometry transitions from Euclidean to Lorentzian signature. The Euclidean trick can sound abstract, so anchor it in imagery. Picture a four-dimensional analogue of a smooth cap, like a dome that closes without a seam. Near the cap, the direction we later call time behaves more like another spatial direction, until the geometry opens into expansion. If we could fly a camera through that mathematical landscape, the motion would feel like drifting over a rounded hill. There would be no sudden cliff labelled t=0, only a smooth change in how directions behave. The proposal tries to replace an abrupt beginning with a gentle geometric transition. The no-boundary idea aims to avoid a singular start by removing the boundary condition that creates it. It replaces initial time with a regularity condition on the geometry. The universe is finite in extent, but not bounded by a prior moment. These proposals differ in technical details and in what they weight as probable. Some favour larger amounts of inflation, some favour less, depending on how measures are chosen. The measure problem is not a footnote. It shapes what the theory predicts. A measure is, in effect, a rule for comparing infinities and assigning relative likelihoods. In cosmology, that is treacherous, because many scenarios generate vast, even unbounded sets of possibilities. The mathematics can produce answers, yet the interpretation can remain fragile. Both approaches share a narrative goal. They try to make the beginning a calculable transition, rather than an undefined singularity. They try to keep quantum mechanics and gravity consistent without assuming a classical time parameter at the start. But we must separate what the mathematics says from what the words suggest. A wave function is not a camera recording a past event, and it is not a diary of what really happened. A path integral is not a literal sum over real histories we could have watched. These tools are ways of computing amplitudes, and amplitudes are not certainties. They encode tendencies, interference, and probability weights, which only become classical facts in a regime where decoherence and coarse graining make alternatives effectively separate. Even then, the language of creation is metaphor stretched over equations. When we say the universe came from nothing, we are translating equations into metaphors. The equations still assume a framework of laws, a space of possible states, and a rule for assigning amplitudes. The metaphysical question of why those laws exist is not answered by writing them down. This is where causality comes under pressure. In ordinary reasoning, a cause precedes an effect in time, and we imagine a chain of earlier events. If time is part of the universe, then precede may be undefined at the boundary. In classical cosmology, we label events by cosmic time, and we can ask what happened earlier. In quantum cosmology, the fundamental equation may not contain time at all. Time can appear only as an emergent parameter, defined by correlations between degrees of freedom. This is the problem of time, and it is not a semantic trick. In general relativity, time is coordinate-dependent and tied to geometry. In quantum mechanics, time is an external parameter that drives evolution, and the system is described at each moment. Putting them together breaks the usual division. If the universe is the entire system, there is no external clock to reference. Any clock must be built from internal variables, like a field that changes monotonically as the universe expands. Then, time becomes a relational concept, not a background stage. One part of the universe can serve as a clock for another part, because their states are correlated. We recover a sense of before and after, but it is derived rather than fundamental. In that setting, asking what happened before the universe began can be like asking what is north of the North Pole. The grammar assumes an axis that the model does not provide. The question may still point to something real, but it may be misposed. This does not mean physics becomes mystical. It means physics becomes careful about what is operationally definable, because definitions are tied to measurement in principle. If no observer and no clock exist outside the universe, then outside time is not a measurable domain. Yet the urge to ask for a cause does not disappear, because it is how human explanation usually works. We can try to generalize causality beyond time ordering, replacing earlier event with deeper constraint. We can talk about explanation as selection, where laws and boundary conditions restrict what can occur. In that view, the cause of the Big Bang is not an earlier push. It is the rule that assigns amplitudes to possible universes and the condition that selects a particular branch. Explanation becomes more like deriving a pattern than tracing a shove. But even that shift has limits, because a boundary condition can be postulated without being derived. Physics can compare proposals by internal consistency and by indirect consequences, but it cannot yet test the boundary directly. We are still building the bridge between mathematical elegance and empirical access, so we keep two claims separate, because mixing them creates confusion. First, vacuum is not nothing, and quantum fields make emptiness active. Second, quantum cosmology can replace a classical singularity with a quantum boundary condition, but it does not automatically answer why there is a law-like framework. Now, connect this back to inflation, because inflation is still our best bridge between microphysics and the large-scale universe. Many quantum cosmology proposals naturally feed into inflation, because a small vacuum-dominated universe inflates easily. Inflation then magnifies a tiny quantum beginning into a classical-looking cosmos. In images, the transition is dramatic. A minuscule region, smaller than an atom, becomes a ballooning expanse, smoothing wrinkles and diluting unwanted relics. Quantum fluctuations, initially microscopic, are stretched into the seeds of cosmic structure, later visible as temperature variations in the CMB. If we linger on those fluctuations, the visuals become almost intimate. A faint, grainy pattern on the CMB sky is the fossil of quantum uncertainty, amplified to cosmic scale. It is a reminder that the vacuum's jitter is not confined to laboratories. It may be written across the universe. That sounds like progress, but it also sharpens the tension. If inflation is driven by vacuum-like energy, then vacuum structure is central to the origin story. Yet vacuum energy is also the quantity we least understand, given the cosmological constant problem. So the beginning becomes a question about the vacuum's meaning at extreme scales. Is vacuum energy a calculable property of fields, or an effective parameter that emerges from deeper physics? Is the vacuum stable, metastable, or one of many possible phases? In high-energy theory, vacua can be multiple, like different minima of a potential landscape. Transitions between vacua can occur by tunneling, producing bubbles of new phases. That language echoes eternal inflation, where bubble universes form in a larger inflating background. Even within a single theory, the word vacuum can hide diversity. Different vacua can have different symmetries, different particle masses, and different effective constants. A vacuum is less like empty space and more like a material phase. Ice, water, and vapor are all water, yet they behave differently. That analogy matters because phases are about organization, not about adding new substances. The vacuum can be organized in different ways, with different low-energy consequences. When cosmologists speak of a vacuum, they may be describing a particular phase of the underlying fields, but the documentary must keep its footing. Landscapes and multiverses are motivated by some frameworks, yet they remain speculative. Their status depends on whether they yield testable signatures, not on how well they fill explanatory gaps. So we return to what is measurable and what is inferred, because that is where science earns its authority. Vacuum fluctuations are real in laboratory contexts constrained by precision experiments. Vacuum energy as dark energy is inferred cosmologically with high confidence, even if its microphysical origin is unknown. Quantum creation proposals are mathematical attempts to extend our models past the classical boundary. They are not confirmed events in a recorded past, yet they are disciplined ways of asking what replaces a singularity. They also remind us that our everyday metaphors may be the wrong tools. The climax of this chapter is not a new answer, but a sharper question. If time is emergent, then beginning is not a moment inside time. It is the point where time itself becomes a useful approximation. That reframes the central question in a disciplined way. If the Big Bang marks the beginning of our observable universe, science can model the hot expansion after reheating with impressive detail. Science can propose quantum boundary conditions that avoid a singularity, but it cannot yet say what it means for laws to operate without space-time. So what caused the Big Bang may not be a cause in the everyday sense. It may be a transition described by a quantum state, where classical time and classical space are outputs, not inputs. The universe may not have a before that can be placed on a timeline, and yet, the discomfort remains productive, because it points to what we do not understand. If nothing is not empty, then origins are not a jump from 0 to 1. They're a question about which structures are fundamental and which are emergent. Pause on that word, emergent, because it changes the mood of the mystery. Emergence means that something can be real and robust, even if it is not basic. Temperature is real, yet it emerges from molecular motion, and time may be similar. If time emerges, what else might be emergent alongside it? Causality, locality, even the idea of a smooth continuum. These are not new claims, but the natural pressure points of the frameworks we have already introduced. The deeper we push toward the boundary, the more our familiar categories begin to wobble. Now we pivot toward alternatives that try to remove the beginning entirely. If a one-time origin makes causality and time collapse into paradox, perhaps the universe did not begin. Perhaps it transformed. Bounce models replace the singular start with a contraction followed by expansion. Cyclic models replace a single origin with repeated phases, where each era inherits conditions from a previous one. These scenarios still face hard constraints, but they shift the question from creation to transition. A bounce must confront the same difficult physics we have been circling. It needs a mechanism that avoids a singularity, often requiring quantum gravity effects or exotic effective stresses. It must also preserve the successes of the hot Big Bang, including nucleosynthesis and the CMB. Visually, a bounce is a slow tightening of the cosmic fabric, galaxies drawing closer in a dimming sky. Then, at the crucial moment, the contraction halts, not by classical collapse, but by new physics, and the fabric relaxes into expansion. The beginning becomes a turning point rather than an edge. Cyclic models add their own demands. They must explain how entropy behaves across cycles, and how each new phase resets conditions without erasing structure entirely. They are not an escape from hard questions, but a different way of organising them. That is the setup for the next chapter's move. If quantum beginnings strain language, then a universe without a first moment may be conceptually cleaner. The mystery deepens, but it also becomes more precise, because we know what we are trying to avoid. We end with the hook, now sharpened by physics rather than softened by metaphor. Before the first star, before the first atom, before space could stretch or time could tick, there was no where for anything to be. And yet something happened, or something like happening emerged. The Big Bang is not the final answer to origins, but the first page of a deeper story. As we push toward the Planck era, the question what caused the Big Bang transforms into what is time, what is nothing, and what laws, if any, can exist without a universe to contain them. The Big Bang still looks like an edge in our equations, even after inflation and quantum beginnings. On a chalkboard, it appears as a hard boundary, an instant where density, temperature, and curvature rush toward infinity. In practice, that edge is a warning light, because infinities usually mean we pushed a theory beyond its domain. General relativity is extraordinarily successful, yet it is a classical theory of space-time geometry. When we drive it to extremes, the mathematics can demand values that no measuring device could ever report. A singularity is not a place you could visit with coordinates and a map. It is a signal that the map has torn. We can describe the approach toward that tear, but the tear itself sits outside the theory's promise. If the edge is a sign of missing physics, one escape is simple in spirit, even if it is difficult in detail. Replace a creation event with a transition between phases of the same universe. Instead of time beginning, the story becomes a passage, one regime handing off to another under rules we only partly know. That handoff matters because it changes what initial conditions even mean. In the standard picture, we choose a starting slice and evolve forward. In a transition picture, the state after the handoff is inherited, constrained, and possibly filtered by the prior phase. The Big Bang becomes less like a birth certificate and more like a scar, evidence of something that happened, even if we cannot yet replay it. Now we pivot toward alternatives that try to remove the beginning entirely. Bounce and cyclic models keep the hot early universe we can test yet deny a singular start. They answer the cause question by pointing to a prior phase, or by making time effectively unbounded. The ambition is not merely metaphysical, it is to keep physics continuous where classical equations break. A big bounce begins with contraction rather than expansion, and it ends with re-expansion. The story runs contraction toward a minimum size and maximum density, then a reversal. Visually, imagine a cosmic hourglass turned on its side, space narrowing to a throat, then widening again. The turning point is not a classical rebound, because classical gravity tends to focus and collapse. In animation, the galaxies would not simply drift inward like dust in air. Distances shrink everywhere at once, as if the grid of space is being steadily tightened. Background light blue shifts, wavelengths compress, and the universe's temperature climbs as the scale factor falls. The scene becomes brighter and harsher, until the familiar rules of matter begin to blur. In general relativity with ordinary matter, contraction drives curvature and density upward until geodesics end. Those geodesics are the paths free-falling observers would follow, and their termination is the technical sign that space-time has become incomplete. The singularity theorems warn that, under broad conditions, collapse is unavoidable. A bounce, therefore, demands a violation of at least one assumption, often through new high-density physics. Those assumptions are worth lingering on, because they are not arbitrary. The theorems typically require energy conditions, roughly that energy density is positive and gravity is attractive in the usual way. They also assume a classical space-time geometry that can be smoothly extended. If quantum effects or exotic stress energy violate those conditions, the conclusion can be evaded, at least on paper. Energy conditions sound abstract, yet they encode a common-sense expectation. If you squeeze matter, it should not respond by producing negative gravity that pushes back harder than the squeeze. But quantum fields can violate some of these expectations in limited ways, and effective theories can mimic repulsion without literal negative mass. The question is whether such violations can be large, stable, and consistent enough to carry an entire universe through a turnaround. One route is quantum gravity producing effective repulsion at extreme density. The claim is not that gravity changes sign in everyday conditions, where Newton and Einstein work exquisitely well. The claim is that quantum geometry or quantum stress corrections alter the Friedmann equations near the Planck regime. That regime is defined by the Planck length and Planck time, scales so small that space-time itself may behave more like a quantum medium. At the Planck length, about 10 Nigel 35 meters, our usual notion of distance becomes slippery. At the Planck time, about 10 to 43 seconds, even the idea of a smooth time coordinate can become an approximation. These are not just tiny numbers for dramatic effect. They mark where quantum fluctuations of geometry are expected to compete with the classical curvature that general relativity describes. In many bounce sketches, the effective energy density reaches a critical value, then the expansion rate stops decreasing. The Hubble parameter passes through zero, and the scale factor reaches a non-zero minimum. That minimum is the key departure from the standard Big Bang picture, because it replaces zero size with small but finite. After that, the universe expands into a hot phase that can resemble the standard Big Bang. The math is often phrased as a modified Friedmann equation, with an extra term that becomes important only near the critical density. Far from the bounce, the correction fades, and the universe behaves like ordinary radiation and matter cosmology. Near the bounce, the correction can act like a pressure that resists further compression, an effective stiffness in space-time itself. The universe does not hit a wall, but it stops being able to compress in the classical way. For a narrator's eye, the bounce is often shown as a curve that descends, flattens, and rises again. Yet the real object is not a simple curve, it is a dynamical system of matter fields, geometry, and perturbations. The bounce must happen quickly enough to avoid catastrophic instabilities, but gently enough that the later universe is not scarred beyond recognition. That balancing act is where model builders spend their time. A useful visual is to overlay several curves at once, density, curvature, and the Hubble rate, so the audience can see what turning around really means. Density peaks, the Hubble parameter crosses zero, and the scale factor bottoms out without vanishing. If the bounce is too abrupt, it can excite unwanted modes like a struck bell. If it is too prolonged, it can give anisotropies time to grow and dominate. This is where we meet the boundary of evidence and the boundary of theory. We can test the hot expansion after reheating and after nuclear synthesis, because those eras leave measurable relics, light element abundances, the blackbody spectrum of the CMB, and the growth of structure all constrain the thermal history. We cannot yet test the microphysics that would enforce a bounce at Planckian densities. The bounce itself sits behind a curtain of energies far beyond any accelerator. The relics are precise because the early universe was a laboratory that ran the same experiment everywhere. Primordial helium and deuterium depend sensitively on the expansion rate minutes after the hot phase begins. The CMB's near-perfect blackbody spectrum tells us the plasma once reached thermal equilibrium with astonishing uniformity. These are not vague hints, they are quantitative constraints that any alternative must pass. Even so, the curtain is not absolute, because early universe physics can echo forward. The bounce might imprint features in the primordial power spectrum, shift phases of oscillations, or generate specific non-Gaussian correlations. It might also leave behind relic particles or topological defects, which later observations could rule out. The difficulty is that many different microphysical stories can produce similar late-time outcomes. In visual terms, those echoes would appear as faint ripples laid over the CMB's mottled pattern. A small suppression of power on the larger scales could hint at a pre-bounce history. Oscillatory ringing in the spectrum could betray a sharp transition, like a sudden change in the universe's effective stiffness. Yet the sky is noisy, and cosmic variance limits what we can read at the very largest wavelengths. Loop quantum cosmology is a concrete example, presented cautiously as an active research program. It applies ideas from loop quantum gravity to a simplified, homogeneous universe. The simplification is deliberate. One begins with a highly symmetric spacetime to make quantization tractable. Spacetime geometry becomes discrete in a specific technical sense, with area and volume operators having quantized spectra. That discreteness is not like a lattice placed by hand, and it is not a claim that space is made of tiny cubes. It is a statement about measurement outcomes in the theory, where geometric quantities come in quanta, the way energy levels do in an atom. In the background, the mathematical language uses connections and holonomies, objects that track how geometry twists and transports around loops. The word loop is not poetic. It names the variables that replace the metric as the primary degrees of freedom. If the metric is the familiar ruler and protractor description of space-time, holonomies are closer to what you get by walking a loop and seeing how directions change. They encode geometry in a gauge-theoretic way, similar in spirit to how electromagnetism can be described by potentials and phases. This shift is not cosmetic, because it changes what can be quantized cleanly. It also changes what smallest area means, since the spectrum emerges from operators rather than from a grid. In that framework, the classical singularity can be replaced by a quantum difference equation. Instead of a differential equation that drives the scale factor smoothly to zero, the quantum evolution proceeds in discrete steps. The effective dynamics often show a bounce when density approaches a critical value. The bounce arises from quantum geometry corrections that act like a repulsive term in the effective Friedmann equation. One way to picture the correction is as a new pressure that appears only when density becomes enormous. It is not a new force in the everyday sense. It is a bookkeeping change in how geometry responds to energy. In some treatments, the effective energy density is bounded above, preventing the runaway that produces a singularity. The universe can then pass through the high-density region and emerge expanding, with curvature and density finite. This boundedness is conceptually striking because it turns infinite density into maximum density, a ceiling rather than a cliff. The ceiling is typically near, but not necessarily equal to, the Planck density. Below that ceiling, ordinary cosmology returns, and the quantum corrections become negligible. The bounce in this view is not a miracle, just a regime change. The promise is conceptual clarity, because the singularity is not merely hidden behind coordinates. In classical cosmology, one can sometimes mistake a coordinate artifact for a physical blow-up, and careful analysis is required. Here the claim is stronger. The quantum evolution itself remains well defined. The warning is equally clear because symmetry reduction and quantization choices matter. Different treatments can change details of the bounce, and connecting to full inhomogeneous quantum gravity remains unfinished. That unfinished bridge is not a minor technicality. Our universe is not perfectly homogeneous, and the very signals we use to test early physics are small inhomogeneities. A theory that resolves the background singularity must also handle fluctuations consistently, without sneaking classical assumptions back in. Researchers debate which variables should be quantized, which approximations are controlled, and which results are robust. The cautious tone is part of the science, not a rhetorical hedge. Even if a bounce is possible, it must do more than avoid infinity. It must produce the observed near-scale invariant perturbations and the CMB acoustic pattern. It must preserve nuclear synthesis and the later thermal history, and it must not introduce forbidden relics. In other words, it must not only survive mathematics, but also survive the sky. A central challenge is how perturbations cross the bounce. Modes that later seed galaxies must be evolved through a regime where classical spacetime may not apply. In the standard hot Big Bang, we evolve perturbations through radiation and matter domination with well-tested equations. In a bounce, the dangerous moment is the turnaround, where the Hubble parameter passes through zero and familiar approximations can fail. At that moment, the usual notion of a horizon can behave differently, and the bookkeeping of growing and decaying modes can swap roles. Small errors in matching can translate into large changes in the predicted spectrum. Model builders therefore track gauge invariant variables, combinations of perturbations that do not depend on coordinate choices. The hope is to carry something unambiguous through the bounce, even when intuition is unreliable. Some approaches treat perturbations as quantum fields on an effective background, while others demand a fully quantum treatment. The first approach is technically manageable, but it risks missing genuinely quantum correlations between geometry and matter. The second approach is conceptually cleaner, but it can become mathematically heavy and ambiguous. Either way, the goal is the same: predict a primordial spectrum that can be compared to CMB maps and galaxy surveys. There is also a subtle issue of initial conditions, even in a universe without a beginning. In contraction, perturbations can grow, and anisotropies can become dangerous. The classic mix-master behavior, chaotic oscillations in anisotropic cosmologies, lurks as a warning sign. A viable contracting phase must suppress those tendencies, or else the universe becomes a patchwork of violent distortions before any smooth bounce can occur. Mixmaster dynamics are more than a dramatic nickname. In certain anisotropic solutions, different spatial directions alternately contract and expand in a chaotic sequence as the singularity is approached. That chaos can shred the smoothness a bounce needs, turning a clean throat into a turbulent crunch. Any successful model must explain why our universe avoided that fate, or why the bounce mechanism overwhelms it. The cause question also shifts in a bounce universe. The Big Bang becomes the aftermath of a prior contraction, not the first moment. The new question becomes why the prior phase existed, and why it contracted toward a bounce rather than dispersing. The explanatory target moves backward in time, but it does not vanish. Some bounce models start from a universe that is already large and cold, then contracts due to its matter content or modified gravity. In such pictures, the contraction can be triggered by an effective equation of state, a scalar field rolling in a potential, or a change in dominant energy components. Others embed contraction in a larger scenario, like a cyclic sequence of expansions and contractions. In each case, the beginning is traded for a deeper prehistory. Cyclic models sharpen that trade because they aim for an eternal pattern. The universe expands, cools, and structures form, then a mechanism reverses the expansion. After contraction, a bounce or a transition starts a new hot phase, and the cycle repeats. The visual language becomes rhythmic, cosmic breathing, a repeated swelling and tightening across unimaginable timescales. If we could watch from impossibly far away, each cycle would resemble a slow pulse. Galaxies would congeal, burn, and fade while the background light cools toward darkness. Then gradually the trend reverses, and the cosmos begins to draw inward again. The rhythm is hypnotic, yet it must be engineered by physics that does not drift or decay. Historically, the lure of cycles is old, long predating modern cosmology. Philosophers imagined eternal recurrence, while early relativists explored oscillating solutions as soon as Einstein's equations were written down. In the 20th century, cyclic ideas competed with steady-state proposals, and both were pressured by the discovery of the CMB. Modern cyclic models differ by keeping the hot Big Bang evidence, while relocating its start into a transition. The early oscillating models also had a practical motivation. If the universe could avoid a beginning, it could avoid a singularity that many physicists found aesthetically troubling. But aesthetics is not evidence, and the CMB made it difficult to deny a hot, dense past. Cyclic ideas survived by adapting, accepting the hot phase while disputing that it was the first. The appeal is psychological and technical at once, because a cycle can make the universe past eternal. If there is no first cycle, the demand for an initial cause can seem less urgent. Yet the physics becomes harder, because cycles must remain consistent across immense time. A model that works for one bounce must work for an infinite sequence, without drifting into contradiction. Ekpyrotic models are a prominent branch of this family, and they invert inflation's timing. Instead of rapid early expansion smoothing the universe, they propose slow contraction smoothing it. During an ekpyrotic phase, the equation of state is very stiff, and anisotropies can be suppressed relative to the dominant component. Stiff here means pressure is large compared to energy density, a condition that changes how different contributions scale during contraction. The scaling is the technical heart of the argument. In contraction, ordinary matter and radiation tend to make anisotropy and curvature grow dangerously. A stiff component can grow even faster, drowning out those threats in relative terms. The universe may still be contracting, yet the dominant energy behaves like a stabilizing background that keeps the geometry from becoming wildly directional. The key idea is that contraction with a steep negative potential can act as a cosmic iron. It can flatten and homogenize the universe by making curvature and shear subdominant. In plain terms, the smoothing component grows so quickly during contraction that irregularities become comparatively tiny. The horizon and flatness problems are addressed without standard inflation, though hybrid variants sometimes reintroduce inflation later. Those hybrids reveal a pragmatic streak. If one mechanism struggles, another is invited in. To visualize ekpyrosis, imagine a wrinkled sheet being pulled tight, not by stretching outward, but by compressing in a controlled way. The wrinkles do not disappear by magic. They become negligible compared to the dominant stiff component. The contraction is slow in terms of the scale factor, yet it can be powerful in terms of how it reshapes relative contributions. That distinction, slow shrinkage, strong dynamical dominance, is easy to miss without the equations. Ekpyrotic scenarios often connect to brain-inspired pictures from higher dimensional theory. Our visible universe can be a three-dimensional brain embedded in a higher dimensional bulk. A collision or close approach between brains can correspond to the hot Big Bang, interpreted as a transfer of energy into brain matter. The imagery is cinematic, two vast sheets sliding through a higher dimensional arena, their near contact igniting a hot, dense state. In that language, the Big Bang is not creation from nothing, but a brain event. The cause becomes the dynamics of the extra dimension and the brain's potential. The mystery moves from a singularity in 4 dimensions to a geometric process in a larger space. Yet the trade is real, because extra dimensions bring their own questions about stability, compactification, and why we experience only 3 large spatial directions. Cyclic ekpyrotic models extend this into repetition, with brains approaching and separating repeatedly. Each approach heats the brain, producing a new hot phase. Between approaches, expansion can dilute matter and structure, preparing conditions for the next contraction. The cycle becomes a sequence of eras: hot, structured, diluted, then reset, each one echoing the last without being identical. But cyclicity runs into a relentless accounting problem, and it is entropy. In ordinary thermodynamics, entropy tends to increase, and the second law is hard to evade. Entropy is not merely disorder in a vague sense. It counts the number of microscopic configurations compatible with a macroscopic state. If each cycle produces stars, black holes, and radiation, the entropy budget grows, and later cycles should look different. This is the past eternity challenge in operational form. If cycles extend infinitely into the past, why is the universe not already maximally entropic? Why do we see a cosmos with large-scale order and free energy gradients rather than a heat death state? The question is sharpened by what we observe: galaxies still forming stars, temperature differences still driving processes, and a universe not yet equilibrated. Classic cyclic models struggle because entropy accumulation makes each cycle longer and larger. The universe would not repeat exactly, and tracing backward can still lead to a beginning. The cycle becomes an arrow, not a loop, unless a mechanism resets or exports entropy. The phrase resets entropy sounds simple, but it is a demand to reverse the most statistically robust tendency we know. Some proposals attempt to dilute entropy by enormous expansion between cycles. If the universe grows by a large factor each cycle, the entropy density can drop even if total entropy rises. The next cycle can begin in a region that is effectively low entropy per volume, though the global entropy still increases. In effect, the universe makes room for its entropy, spreading it thin across a vastly larger arena. Other proposals suggest entropy is dumped into extra dimensions or into regions that become causally disconnected. In brain pictures, some entropy might leak into the bulk, leaving the brain cleaner. These moves are controversial because they risk hiding entropy rather than explaining its fate. If entropy is merely pushed out of view, the model must still say where it goes and why it does not come back. There is also the question of black holes, which are efficient entropy factories. A cyclic universe must address whether black holes persist across cycles, evaporate, or are destroyed in a bounce. Hawking radiation suggests evaporation over immense times, but those times can be far longer than a cycle, unless the cycle is extraordinarily long. Each option carries assumptions about quantum gravity and about how information and entropy behave. Even if entropy can be managed, cyclic models must generate the right primordial perturbations. Inflation produces nearly Gaussian, adiabatic, nearly scale-invariant scalar fluctuations with a small red tilt. Alternatives must match those successes while predicting distinguishing deviations. The bar is high because the data are precise, and the CMB is unforgiving of sloppy early universe stories. Ekpyrotic contraction can generate nearly scale-invariant perturbations through entropic mechanisms. Typically, multiple fields are used, and isocurvature perturbations are converted into curvature perturbations. The conversion process can imprint distinctive non-Gaussianity and correlations. In plain language, fluctuations that begin as composition differences between fields can later become density differences that shape galaxies. The details matter because the CMB does not only measure a slope, it measures phase coherence in acoustic peaks, the relative heights of harmonics, and correlations between temperature and polarization. Any alternative must reproduce that delicate pattern, not just a rough scale invariance. This is why perturbation theory is not an optional add-on, it is the core test. This is where observational fingerprints become the battleground. Non-Gaussianity is a key discriminator, because many ekpyrotic mechanisms predict larger local type non-Gaussianity than simple slow-roll inflation. Local type refers to a specific shape of the three-point correlation function, strongest when one wavelength is much longer than the others. Current constraints are tight, yet not final, and model building often adapts to survive. When constraints tighten, models do not simply die, they evolve. Parameters are adjusted, conversion mechanisms are refined, and new consistency conditions are derived. That process is not a weakness by itself, because science often progresses through refinement. The danger is over-flexibility. If a framework can fit anything, it predicts nothing. Tensor modes are another sharp test. Inflation generically predicts a stochastic background of primordial gravitational waves with amplitude tied to the energy scale. Many ekpyrotic and some bounce models predict a very small tensor signal at CMB scales, often far below near-term reach. The reason is structural. Slow contraction does not amplify tensor modes the way accelerated expansion does, so a detection of primordial B-mode polarization at a significant level would pressure many cyclic alternatives. It would not instantly prove inflation, because foregrounds and secondary effects must be controlled, yet it would narrow the viable space, because alternatives would need extra mechanisms to raise tensors without ruining other successes. A continued non-detection does not prove a bounce, but it shifts the plausibility landscape. The tension becomes empirical, not merely philosophical. Competing stories about the beginning or non-beginning must eventually cash out as patterns in the sky. The CMB is a fossil light, and large-scale structure is a fossil distribution of matter. Together they act like a long-exposure photograph of the early universe's statistics. Spectral tilt and running also matter, because different mechanisms produce different deviations from scale invariance. Inflation's measured tilt, slightly red, is consistent with many slow-roll models. Ekpyrotic scenarios can produce similar tilts, yet the parameter dependence and correlated predictions can differ. Running, the change of tilt with scale, can become a subtle clue, especially as datasets expand. Large-scale structure adds another arena, because primordial statistics propagate into galaxy clustering. Surveys measure the matter, power spectrum, B-spectrum, and scale-dependent bias. Non-Gaussian initial conditions can alter halo formation in characteristic ways, providing independent cross-checks beyond the CMB. The point is not that galaxies remember the bounce directly, but that they remember the statistics of the seeds. Future CMB polarization missions and ground-based arrays aim to push tensor limits and foreground separation. The observational challenge is partly astrophysical, because dust and synchrotron emission mimic polarization patterns. Next-generation galaxy surveys aim to map enormous volumes with precise redshifts. Together, they can test subtle signatures that separate inflationary, bouncing, and cyclic predictions. Yet we must keep the discipline learned earlier, because evidence is not evenly distributed across ideas. Inflation has a mature pipeline from assumptions to observables, even if its origin remains uncertain. Bounce and cyclic models are diverse, and their predictions can be more model-dependent, which complicates clean falsification. Diversity is not a flaw, but it does make the scientific conversation noisier. This returns us to inflation's missing origin story, now reframed by competition. If inflation needs special initial smoothness, a prior contracting phase might supply it. If reheating uncertainty blurs inflation's mapping from scales to E-folds, alternatives exploit the same observational margins. The debate becomes less about slogans and more about which uncertainties are tolerable, but alternatives inherit their own initial condition questions. A contracting universe must be smooth enough to avoid chaotic mix-master behavior near contraction. A bounce must avoid instabilities and ghosts in effective theories, and it must not amplify anisotropies into disaster. Ghosts are not metaphors here. They are degrees of freedom with wrong-sign kinetic terms that signal a sick theory. There is also the issue of matching conditions across the bounce, a technical phrase with major consequences. How exactly do you connect pre-bounce perturbations to post-bounce observables without ambiguity? If the bounce is short and violent, it can scramble phases and generate features. If it is long and smooth, it may preserve more memory, but it must remain stable throughout. The deeper point is that each escape route changes what counts as an explanation. A bounce explains the Big Bang by pointing to a prior contraction, which is a causal story inside time. A cyclic model explains by repetition, which can make cause feel like pattern rather than event. The word because starts to mean because it repeats, not because it began. A brain collision explains by embedding our universe in a larger geometry, which shifts the cause into extra dimensions. A quantum bounce explains by modifying the rules of space-time at high density, which shifts cause into the structure of the laws. Each move is coherent, yet each move changes the shape of the question we're allowed to ask. To understand what we can ask, we start with what we can calculate. We can calculate how a given bounce modifies the primordial spectrum, and we can compare it to the CMB. We can calculate how non-Gaussianity propagates into galaxy statistics, and we can test it with surveys. These are not philosophical exercises. They are pipelines from equations to maps. But we cannot yet calculate the full Planck regime dynamics from a confirmed theory of quantum gravity. We cannot yet derive a unique bounce mechanism from first principles. The cause question therefore becomes conditional, and the conditions are the models themselves. In a sense, each model proposes a different grammar for what before and because can mean. This chapter is the climax because it reveals a pattern across competing ideas. When we try to avoid a singular start, we either add a prior phase, or we redefine the boundary as a condition. In both cases, the Big Bang stops being the first event and becomes a hinge. The hinge is a transition point where our tested physics meets a region of extrapolation. The hinge can be a bounce, a collision, or a quantum boundary. Yet the hinge must leave traces. The universe is not obliged to preserve those traces, because violent transitions can erase memory. The scientific hope is that some information survives in the larger scales and in primordial statistics. The larger scales are precious because they have had the least time to be processed by later astrophysics. So the narrative tension becomes a comparison of bets. Inflation bets on a brief accelerated expansion and small non-Gaussianity with a possible tensor signal. Ekpyrotic and cyclic models bet on smoothing by contraction, distinctive non-Gaussianity, and typically tiny tensors. Bounce models bet on quantum gravity resolving singularities, with possible features in the spectrum from pre-bounce physics. Brain-inspired models bet on higher dimensional dynamics that can mimic a hot beginning. Each bet has a cost in assumptions, and each cost is part of the explanation. A model that removes one mystery can introduce another, sometimes smaller, sometimes larger. The honest question is which mysteries are structured enough to be attacked scientifically. We end by turning the central question one more time because the alternatives do not eliminate it. If the Big Bang marks the beginning of our observable universe, what can science say about the cause or conditions that led to it? Bounces and cycles suggest that the cause might be earlier in time, yet the chain can still demand a first link. Even an infinite chain raises a quiet question about why the chain exists at all. And if the chain has no first link, then explanation becomes something else. It becomes a boundary condition, or a law-like constraint, or a selection principle. In that framing, the universe is not started, but specified, as if the deepest answer is a rule rather than an event. The final chapter confronts the hardest version of the mystery, after every escape has been tried. After touring possibilities, we face the question beneath the question. Are we asking for a physical cause inside time, a boundary condition that replaces time, or something beyond what science can meaningfully answer? The Big Bang remains the first page we can read, but not necessarily the first page that exists. And the more we learn to read the sky, the more we discover how much of the book is still sealed. We return to the opening hook and treat it as a test of language, not just a dramatic question. Before the first star, before the first atom, before space could stretch or time could tick, we asked what could cause a beginning. On screen, the familiar images of galaxies fade away, leaving a dark frame that is not emptiness but uncertainty, an unlit stage where our usual verbs may not apply. Now we answer with a map, not a single cause, because cosmology rarely rewards one-word explanations. The Big Bang remains the earliest chapter we can reliably read, because multiple lines of evidence converge on a hot, dense past. That convergence matters because it is how science distinguishes a shared story from a convenient metaphor. Cosmic expansion is measured across the sky through redshift and distance indicators, and the pattern is not subtle. Spectral lines shift toward longer wavelengths as space itself expands, and the shift grows with distance in a way first systematized by Hubble and his contemporaries. In visuals, the universe becomes a grid that gently stretches, and the light traveling through it lengthens like a note sliding downward. Distance is not guessed, it is built from ladders of calibration that link nearby geometry to faraway brightness. Cepheid variables pulse with a period, luminosity relation, and Type Ia supernovae act as standardized explosions once corrected for light curve shape and color. Each rung adds uncertainty, yet the overall trend persists, and the sky keeps insisting on expansion. The cosmic microwave background is a second pillar, and it arrives like a photograph taken when the universe first became transparent. The CMB is a near-perfect blackbody, with a temperature of about 2.7 Kelvin, and its spectrum is so precise that it reads like a laboratory curve. On screen, a smooth Planck curve overlays the darkness, and then the map appears, mottled by tiny temperature variations at the level of tens of microkelvin. Those mottles are not random noise, because their angular pattern contains acoustic peaks that encode early plasma physics. Before atoms formed, the universe was a hot ionized fluid of electrons, protons and photons, and light could not travel freely. Gravity tried to compress overdense regions while radiation pressure pushed back, and the competition set up sound waves in the primordial plasma. When the universe cooled enough for electrons to bind to nuclei, photons decoupled and streamed outward, carrying a frozen imprint of those oscillations. The peaks in the CMB power spectrum are the harmonic notes of that early sound, and their spacing reveals the geometry of space. In the visuals, ripples spread across a luminous fog, then abruptly stop, captured as a pattern on a spherical shell. Light element abundances provide a third line of evidence, and they are a chemical fossil rather than a photograph. In the first few minutes, temperatures were high enough for nuclear reactions, but the window was brief because expansion cooled everything rapidly. Big Bang nucleosynthesis predicts specific ratios of hydrogen, helium, deuterium, and lithium, and those ratios can be checked against observations in ancient gas clouds and old stars. The match is not perfect, and the tensions sharpen rather than erase the picture. Deuterium agrees strikingly well with standard predictions, and helium is broadly consistent once systematics are handled carefully. Lithium remains stubborn, and that stubbornness is useful because it forces us to ask whether we misunderstand stellar atmospheres, nuclear rates, or early universe ingredients. This arc matters because it separates confidence from extrapolation, and it teaches a discipline of stopping points. We can run the universe backward with the Friedmann equations, translating expansion history into densities and temperatures. Yet the closer we approach the Planck regime, where quantum effects on spacetime should dominate, the more the mathematics warns us that we are extending a tool beyond its tested range. The singularity is not a photographed event, and it is not a timestamp on a cosmic calendar. It is geodesic incompleteness in classical general relativity, meaning that some paths of freely falling observers cannot be extended indefinitely into the past. That is a precise statement about the limits of the model, and it likely marks incomplete physics rather than a literal point of infinite density. Historically, this distinction mattered because singularities were once treated as signs of failure, not features to celebrate. The singularity theorems of Penrose and Hawking showed that, under broad conditions, classical relativity predicts such edges. The theorems did not tell us what happens at the edge, and they certainly did not provide a mechanism for a beginning. Here we meet the boundary of evidence and the boundary of theory. The data anchor a hot beginning after reheating, while the cause question pushes into quantum gravity, where time and vacuum become slippery. In visuals, the crisp CMB map dissolves into a grainy, abstract animation, as if the screen itself cannot decide how to draw before. Inflation remains the leading candidate for what happened before the Hot Big Bang, and its appeal is partly architectural. It explains the horizon problem by allowing distant regions to share a common causal past, and it explains flatness by stretching curvature until it becomes nearly imperceptible. It also dilutes unwanted relics, like hypothetical monopoles, by expanding them away to irrelevance. The core idea is accelerated expansion driven by an energy component with negative pressure, often modelled as a slowly rolling scalar field. In plain terms, it is a brief era when the universe's expansion sped up dramatically, smoothing and enlarging a tiny patch. On screen, a small bright region balloons outward, and the surrounding irregularities flatten like wrinkles pulled taut. Inflation does more than smooth, because it turns quantum fluctuations into the seeds of structure. Vacuum fluctuations are unavoidable in quantum field theory, and during inflation they are stretched from microscopic scales to astronomical sizes. When inflation ends, those fluctuations become classical density perturbations, and gravity later amplifies them into galaxies and clusters. The strongest inflationary success is statistical, and statistics are the language of the early universe. The perturbations are nearly scale invariant, meaning their strength changes only slowly with wavelength. They are nearly Gaussian, meaning the map's fluctuations resemble a random field defined mostly by a two-point correlation. They are mostly adiabatic, meaning different components fluctuate together rather than independently. These properties are not arbitrary, because they arise naturally from simple slow-roll dynamics. A gently sloped potential produces a spectrum with a slight tilt, and the tilt has been measured. The near Gaussianity reflects the weakness of interactions during inflation, and the adiabatic nature reflects a single dominant clock controlling the expansion. Yet inflation is not fully pinned down, and the gaps are not cosmetic details. We still lack a confirmed inflaton, a unique potential, and a measured tensor signal, and reheating uncertainty blurs the mapping from models to observables. Reheating is the handoff, when inflation's energy converts into the hot particles that later form the plasma we infer from the CMB. That handoff is crucial, because it sets the initial conditions for the standard Hot Big Bang phase. Different reheating histories change how many E-folds of inflation correspond to the scales we observe today. In visuals, the smooth inflationary expansion ends in a burst of particle production, like a silent fireworks display that becomes the first thermal scene in the film. The missing origin story remains, and it is where inflation's elegance becomes a challenge. Inflation can start only if a patch is smooth enough, and the field is placed on the right part of its potential. Those requirements can feel like fine-tuning relocated, because the theory that explains one set of initial conditions appears to assume another. This is not a fatal flaw, but it is a real question about explanatory depth. Does inflation make the universe generic, or does it merely shift the specialness into a prior state? When we say natural, do we mean mathematically common, physically stable, or simply compatible with what we observe? Eternal inflation sharpens the tension, because it changes what prediction means. If inflation is generically self-reproducing, then quantum fluctuations can keep some regions inflating even as others end. The result is a vast mosaic of bubble-like regions, each with potentially different low-energy properties, and global predictions depend on measures over enormous possibilities. That dependence turns testability into the central question, because measures can be chosen in ways that change what is likely. In visuals, the camera pulls back from one expanding region to many, like foam forming and reforming, and the narration pauses on the discomfort of infinities. If everything happens somewhere, what does it mean to explain what happens here? Alternatives try to remove the singular start rather than decorate it, and they do so with different risks. Bounce and cyclic models replace a beginning with a transition, where contraction leads to expansion. They must survive the CMB's phase coherence, because the observed acoustic peaks require a very specific pattern of correlated perturbations. They must also satisfy nucleosynthesis constraints, because the early thermal history cannot be arbitrarily rewritten. In many bounce scenarios, avoiding instabilities or singular behavior requires exotic matter components or modified gravity effects. On screen, the universe contracts like a slow inhale, reaches a tight, bright moment, then expands again. Yet the visuals emphasize how delicate that turning point must be. Quantum cosmology tries to replace the classical edge with a quantum description, and the shift is conceptual as much as mathematical. Tunneling and no-boundary ideas treat the beginning as a boundary condition on a wave function, not an event inside time. The goal is not to describe a first moment, but to define allowed histories and their probabilities. In the no-boundary picture, space-time can behave like a smooth geometry without an initial edge, analogous to how a sphere has no special starting point at the pole. That analogy can mislead if taken literally, yet it captures the intention. Remove the singular boundary by changing what counts as a beginning. In visuals, a sharp corner in a graph is replaced by a rounded curve, and the camera lingers on the difference between a limit and a wall. These proposals are plausible and mathematically disciplined, yet unconfirmed, and their uncertainty is structured rather than vague. They often depend on mini-superspace approximations, where only a few degrees of freedom are quantized while others are ignored. They also involve contested measures, and assumptions about what counts as a vacuum when spacetime itself is dynamical. To understand what we can ask, we start with what we can calculate. Every candidate origin story must connect to relic signatures, because cosmology is constrained by fossils rather than laboratory reruns. We do not get to reset the universe, so the sky becomes our archive, and statistics become our forensic toolkit. At this point, the documentary has uncovered 3 distinct meanings of cause, and each meaning carries a different demand for evidence. The first is a dynamical trigger, where some physical process initiates expansion or initiates inflation. This is the most intuitive meaning, because it resembles everyday causation, one event producing another. In that category, the cause is an event-like mechanism, and it must be described by equations of motion. It could be a field transition, a vacuum decay, a phase change, or a bounce in stability that flips contraction into expansion. The key requirement is temporal ordering, because the explanation assumes a before that can influence an after. Vacuum decay, for example, is often modelled as a quantum tunneling event from a metastable state to a lower energy state. In field theory, such transitions can nucleate bubbles that expand at near light speed, converting one phase into another. On screen, a small bubble forms in a glowing medium and races outward, leaving a different texture behind. The second meaning is a boundary condition, and it sounds less like a push and more like a rule. The cause is not a trigger but a specification, like an initial quantum state, a regularity condition, or a selection rule on allowed histories. In this view, the universe is not kicked into existence, it is described by a state that makes later events probable. In that category, explanation resembles constraint rather than chronology, and the distinction matters for how we judge success. A boundary condition can be elegant and predictive, yet it can also be arbitrary if it has no deeper justification. The question becomes whether the condition follows from a principle, or whether it is simply chosen because it fits. The third meaning is a reframing where before is undefined or unnecessary, and this is where language begins to strain. If time is emergent, then asking what happened before the Big Bang can be a category error. Before presumes a timeline, and the proposal is that the timeline itself is a derived feature of a deeper description. This is not a retreat into mysticism, and it is not a permission slip for anything goes speculation. It is a reminder that causality in physics is normally defined within spacetime, and the question may fail when spacetime is what needs explaining. In visuals, a clock face appears, then dissolves into a network diagram, as if time is being assembled from relationships. So what counts as an answer depends on which kind of cause we demand, and that choice is often implicit. If we demand an earlier in time trigger, we may be asking for a clock outside the universe. We may also be demanding a background stage on which the universe begins, even though the universe is supposed to include the stage. If we accept a boundary condition, we still face a deeper question, and it is not easily dismissed. Why that condition and not another, and what principle would make it more than a convenient postulate? In physics, boundary conditions can be justified by symmetry, minimality, or consistency, but those words can hide as much as they reveal. If we accept reframing, we must still explain why time emerges with the properties we measure. We must recover the arrow of time, the growth of entropy, and the stability of classical spacetime. We must also explain why the emergent time behaves locally, like the smooth parameter used in relativity and quantum theory. This is where humility becomes a scientific strength, because it prevents us from confusing a boundary with a blank check. Not knowing is not failure when it is a precise statement about which claims are testable and which are not. The discipline is to say, clearly, what would count as evidence and what would merely be interpretation. Science earns authority by narrowing possibilities with data, and the early universe has been unusually generous in leaving traces. It tells us which stories survive the sky, which stories are flexible to the point of emptiness, and which stories are waiting on new instruments. In visuals, competing curves and parameter spaces appear, and the allowed regions shrink as new measurements arrive. The next question is what evidence could shift the story, because the frontier is not only theoretical. The early universe is not only a past era, it is a set of statistical patterns that future surveys can read more sharply. The difference between plausible and compelling may come down to a handful of faint signals buried in noise. Primordial gravitational waves remain a decisive target, because they would be a direct imprint of inflation's energy scale. A robust detection of large-scale B-mode polarization would strongly support inflationary models that generate observable tensor modes. It would also rule out many slow contraction alternatives, which typically predict a much smaller tensor background. B-modes are hard because the signal is faint and the foregrounds are bright. Dust in our own galaxy emits polarized light, and gravitational lensing converts some E-modes into B-modes, creating a confusing background. On screen, the clean theoretical pattern is overlaid with swirling foreground textures, and the narration emphasizes the patience required to separate them. A continued non-detection also speaks, and it is not merely an absence. It would push inflation toward lower-scale models and increase pressure to explain why tensors are suppressed without losing the observed scalar spectrum. Some models can do this naturally, while others require additional structure, and the data would force that distinction into the open. Non-Gaussianity is another discriminator, and it is a subtle test of interactions in the early universe. Inflation in its simplest forms predicts very small non-Gaussianity because the fluctuations are nearly free and weakly coupled. Many multi-field, bouncing, or ekpyrotic mechanisms can generate larger shaped signals, leaving patterns beyond the two-point function. Future constraints on bispectra and scale-dependent bias can separate mechanisms, because different dynamics leave different triangle fingerprints. The goal is not a single number, but a pattern across configurations that reveals how modes interacted when they were born. In visuals, triangles of different shapes appear on a graph, and each lights up with a different predicted intensity. Relic particles could also matter, because they would be direct messages from high-energy epochs that we cannot reproduce. Axion-like fields could leave isocurvature traces or alter small-scale structure, while dark radiation would shift the expansion rate and the damping tail of the CMB. Primordial black holes, if they exist in the right mass ranges, could act as both relics and constraints. Topological defects, such as cosmic strings, are another possibility already hinted at by high-energy symmetry breaking. They would leave distinctive signatures in CMB maps and gravitational wave backgrounds, like thin discontinuities or a stochastic hum. On screen, a faint line cuts across a simulated sky map, and the narrator treats it as a hypothetical clue. Even null results are informative, because they are not empty outcomes in a constrained theory space. Each non-detection tightens the allowed space of models and forces origin stories to become more specific, rather than more poetic. In science, being wrong in a measurable way is often more productive than being vague in an untestable way. The 21-centimeter line offers a new window on the cosmic dark ages, and it is a window with depth. Mapping neutral hydrogen across redshift can probe small-scale power, heating histories, and exotic energy injection. The signal is difficult, buried under bright radio foregrounds, yet its promise is extraordinary. That matters because the CMB is a two-dimensional surface of last scattering, a single shell we observe from one time. The 21-centimeter signal is a three-dimensional tomographic record, potentially sensitive to features inflation might hide. In visuals, the CMB becomes a sphere around the viewer, then the 21-centimeter maps appear as stacked shells, forming a luminous volume. Next-generation surveys will map early structure with unprecedented volume, and volume is statistical power. Galaxy clustering, weak lensing, and high redshift traces can test primordial statistics beyond the CMB's cosmic variance limits. They can also cross-check one another, reducing the chance that a single systematic error drives the conclusion. Weak lensing, in particular, measures the integrated distortion of light by intervening matter, effectively mapping the distribution of mass rather than just luminous galaxies. Galaxy clustering measures how matter clumps on different scales, and both are sensitive to the initial spectrum of perturbations. On screen, a web of filaments emerges, and then a transparent overlay shows how gravity subtly shears background images. Together, these observations do not promise a final cause, and the documentary does not pretend otherwise. They promise a sharper boundary between what is compatible with the universe we see and what is not. They turn philosophy-like questions into physics-like questions, at least for a little farther back in time. We also return to the small tensions introduced earlier, because tensions are where models either break or mature. The lithium problem and expansion rate tensions may resolve through systematics, or they may hint at missing ingredients like new particles or early energy components. The point is not to root for a crisis, but to recognize that anomalies are often the first draft of discovery. The expansion rate tension, for example, pits early universe inferences from the CMB against late universe distance ladder measurements. If it persists under improved calibration and modeling, it could indicate new physics that slightly alters the expansion history. On screen, two error bars refuse to overlap, and the narrator lets the discomfort linger. Either outcome is useful because both outcomes teach us how robust our story is. Resolution strengthens the standard model's reliability, while persistence provides a controlled crack where new physics might enter. The crack is valuable only if it is real, which is why the documentary keeps returning to measurement discipline. So the documentary resolves its mystery by clarifying the shape of the unknown and by refusing to confuse mystery with ignorance. The Big Bang is strongly supported as a hot early state, while the singularity is likely a sign that our description ends. The ending is not a failure of curiosity. It is a marker of where new principles must take over. Inflation is compelling but not fully established, and that balance is the honest position. Quantum and bounce models are plausible but unconfirmed, and their diversity makes prediction harder and evidence more crucial. The more options we can write down, the more we need nature to choose for us through data. At the end, the central question changes form, and the shift is the chapter's real conclusion. If the Big Bang marks the beginning of our observable universe, science can describe the aftermath with precision, and it can outline credible prelude candidates. What it cannot yet do is name a unique cause with the same confidence, because the word cause may be doing too much work. The obstacle is not only missing data, it is that cause may mean law, state, or a concept that fails when time is emergent. A dynamical trigger demands a prior time, a boundary condition demands a principle, and a reframing demands a new grammar. The question becomes not only what happened, but what kind of answer can the universe allow? We close by returning to nothing, now stripped of its everyday meaning and its comforting simplicity. In physics, nothing is rarely empty, because vacuum is a state of fields, and fields already assume a framework of rules. Even empty space has fluctuations, symmetries, and energy scales that can, under the right conditions, have consequences. If the deepest origin question asks why there is something rather than nothing, science may answer only part of it, and that partiality is not defeat. It can show that the earliest readable page is not blank, and it can show where the ink runs out. It can also show that the page itself, space and time, may be part of what needs explaining. The haunting part is not that we lack imagination, because imagination has never been in short supply. The haunting part is that the universe may require us to revise what an explanation is, and to accept that some questions must be translated before they can be tested. Translation is not surrender. It is how physics has advanced when old intuitions failed. The universe is not only expanding in space, it is expanding the frontier of what can be asked, and forcing us to separate meaningful questions from familiar grammar. In visuals, the camera drifts outward through galaxies, then through the CMB, and finally into an abstract field of equations that fade into darkness. The final thought is grounded and unsettled, because it respects what we know and what we do not. The Big Bang is the first page we can read, while the question of its cause may teach us what time, nothingness, and physical law really are. And as the screen holds on that last dark frame, we are left with a question that sounds ancient, yet remains, in a precise way, scientific. We followed the universe backward using 3 stubborn clues that agree across independent methods: cosmic expansion, the microwave background's near-perfect blackbody glow, and primordial element abundances. Those pillars make the hot early universe feel almost unavoidable, even as precision tensions like lithium and the Hubble constant whisper that the story is incomplete. and at the sharpest edge, where general relativity predicts a singularity, we met the same warning again and again: our equations are mapping a boundary, not filming an event. From there, every proposed origin story became a test of what can survive contact with data. Inflation explains the horizon and flatness puzzles by stretching space itself, and it turns quantum fluctuations into the seeds of galaxies, yet it also inherits unanswered questions about its start, its end, reheating, and the possibility of eternal inflation. Quantum cosmology asks whether the beginning is better described by boundary conditions than by a trigger, while bounce and cyclic models trade a one-time start for a handoff from a prior phase, then fight to preserve the phase-coherent patterns we see in the CMB. Across all of them, the Planck era remains the fracture line, a regime where space-time may fluctuate, time may emerge, and cause may stop behaving like a simple arrow. Still, the journey leaves us with a hard-earned kind of clarity. Science can say a great deal about the early universe, and it can say exactly where its confidence ends. It can separate evidence from extrapolation, quantify what must be true for each scenario to work, and turn mysteries into targets: B-modes, non-Gaussianity, relic particles, 21-centimeter maps, and next-generation structure surveys. The Big Bang, in that sense, is not the last word on origins. It is the first page we can read with high precision, and the margin where the ink begins to fade. So what could possibly cause a beginning of space and time, and can physics look behind that first flash? After everything we've seen, the most honest answer is that cause may not mean earlier in time, when time itself is part of what begins, and what we call a cause may instead be a law, a boundary condition, or a quantum transition that doesn't sit inside any prior clock. If there is a before, it may not be a place the universe came from, but a deeper description where space-time is emergent and where our familiar questions must be translated. The singularity is not a door we have opened, it is a signpost that says, here the classical story ends, and whatever comes next must earn its reality by leaving fingerprints we can measure. In the end, the Big Bang does not draw a clean line between nothing and everything. It draws a line between what our current physics can explain and what it can only frame, and perhaps that is the real revelation. The closer we get to the Planck era, the more the question transforms from what caused the Big Bang into what is time, what is nothing, and what laws, if any, can exist without a universe to contain them. We began with the image of reality having no stage at all, and we end with a quieter mystery. Maybe the stage and the script were always the same thing, and the deepest beginnings are not explosions but rules. When science finally meets that boundary with new evidence, the answer may feel less like a cause, and more like a new way to understand what it even means to begin. Stay with the data as it sharpens, because the next faint signal we detect may not just refine the Big Bang, it may redefine the word before